Hello. Hello, Dr. Babluji. Hello, Dr. Babluji. Am I audible? Am I audible
Yes,
to
sir.
anyone? Okay, okay. Yeah, thank you. Karthik, YouTube is okay? Is it live?
Wait a minute, sir. I am going to check.
Okay. I think it's live. So, Karthik, I think it's working.
Yes, sir. It is working.
Good morning, Bablu Mukherjee.
Hello, it's not connecting. 1 minute.
Oh, your voice is audible and your video also fine. Only one thing is that you have to share the screen. morning, Babluji. Is it audible? Please come to unmute. Yes, fine. It obvious.
Hello.
Hello, sir.
It's not working here.
Before it was presented, sir, but now it is not, sir.
Yes, it's automatically, is going off. Is
Now it is presented, sir.
now can you see the screen?
Yes, sir, it
Hello.
is visible.
But it's not in. So I am in
Yes,
the.
sir, it is visible.
It is in the mobile. So I am. This way can I present?
You can connect this also and present, sir.
Okay. Okay. So shall I start? So yes,
Make it
basically I am.
10 sir.
Basically, I am presenting from mobile because my laptop is not connecting. So it is connecting, then it is getting off automatically. So, so I start if using this. Is that okay? Sorry, let me check 1 minute. Blank. Sorry.
Karthik, is there any problem?
Sir, Bablu's sir presentation was not connecting, sir.
No, no, it was connected. Just now it was connected, again it went off.
Yeah, only from mobile only I can able to connect. Hello.
Okay, then we'll do one thing. First, till we, till we introduce about you, you can show your video. Later, you can show your presentation.
So now can you see my screen or not?
Yes, yes, yes. Your screen is visible. It shows the title: Semiconducting Nanostructures, Synthesis and Fabricating Devices. It is visible.
Okay, so this way I can present actually.
Yes, yeah, yeah, exactly. In this way, we can start.
Okay. Then okay, I can start. Yes. So let me know when I should start.
Yeah. Please wait for 2 minutes. So we'll start.
Okay.
In between, we'll have a small introduction. Later, we'll start.
Okay. Thank you.
Is it fine?
Yes.
Yeah. Thank you.
Sir, Bablu sir.
Yes. Hello.
Bablu sir,
Yes.
please rotate your mobile, sir, so that it will be in full scale.
So that's the thing.
I mean, what he says to present, you can make it in a horizontal way.
Because it is in the web browser, so I am not able to do. I am trying only that. So
Okay.
in the laptop is not connecting. Some problem there is.
No, actually, I mean, what other faculty colleague is telling that your mobile you can turn on while present your mobile you can turn to horizontal while presenting your
Okay,
session
okay, okay,
so that
okay, okay,
so
okay.
that you are present you can try once also
One
before
minute. Yes, I got it. Hmm.
yeah you can try once.
I need to set something turn on. You know.
No, nothing. You just rotate your mobile 90 degrees. That's enough, I feel.
Yeah, but the skin rotation need to be on before that. So I'm
Oh,
trying.
okay, okay, fine,
Screen.
fine.
There is no. So yeah. No, it's not working here.
Okay. So can you move the slides? I mean, like this?
Yes, yes, yes. I can move like this.
Okay, you just check one. Yeah, it is movable.
Okay.
Not a issue.
Only is not going full screen.
Yes.
Yes, that's the
Sir, if
yeah.
mobile
That
is
full
rotated,
screen.
then it will be more clear, sir.
It is in the mobile, so that's the Google slide. I don't know whether. Mm, So this way only I can present. Mm.
It's okay, not a issue. So, Bhavani madam,
చెప్పండి సార్.
shall we start, madam?
హలో. ఓకే సార్.
Okay, shall I start?
No, 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 no. We'll invite you. Later, you start. So,
Bhaskar sir,
yeah. So that theory,
shall I
sir.
start then?
Yeah. You have to start uh, considering.
Yeah,
I mean,
let's start now then.
I, yeah. Invite all of them and hand over to me. So
Yeah.
I will speak about the few words about the speaker. Then it will be given to the our speaker.
Yeah.
Start, sir.
Okay. Good morning and namaskar all of you. I welcome all the participants, speakers and my department colleague for today's program. Today we'll have 3 talks and a team of our department led by Mr. Bhaskariya, Dr. Bhavani, Dr. Karthik, Raghu Reddy sir and myself will be helping you with the webinar. And out of the 3 talks, it will be the first talk will be Dr. Bablu Mukherjee, second by Dr. V. Divakar Bocha, and third by our beloved ex-director Professor G. Bhagwanayan Garu. I hand over the mic to our beloved Bhaskar sir. He will start the welcoming. Thank you and namaskar. Bhaskar sir, please. Bhaskar sir.
Yes. Good morning, one and all. So, thank you very much, Dr. Tiwari. for inviting all of us for this second day international webinar series on synthesis and characterization of nanomaterials and their novel applications. So I would like to introduce today the first talk, which goes to Dr. Bablu Mukherjee. He is currently working as a research fellow at National Center for Materials, Nano-Architectonics, MANA of National Institute for Material Science, Japan. He did MSc Physics from Indian Institute of Technology, Madras in 2009. He has received his PhD from National University of Singapore in 2013, and he was a JSPS Fellow 2017 at NIMS and Assistant Professor at VIT Vellore in 2017. Then later he did his postdoctoral fellow at IIT Bombay in 2015, and he was also a postdoctoral scientist at George Washington University 2014, and research assistant at NAS. And also earlier he was a DAD fellow in 2009 at Gottfried Wilhelm Leibniz University, Vancouver. His research interests are in the areas of optoelectronics and nanomaterial science, engineering for applications in photodetectors, non-volatile photoelectro memory, nanosensors, and 2D layer materials based optoelectronic devices. Now I welcome Dr. Bablu Mukherjee to present his talk. So over to Dr. Bablu Mukherjee.
And
Thank you.
Yes. Thank you, Bhaskar sir, for your kind introduction and for your invitation to give this international webinar series. So today I will give seminar talk in this topic. Is semiconducting nanostructure synthesis fabricating device for optoelectronic application. So here is the outline of my today talk. So I will first start with semiconducting nanostructure, their introduction, and I will also discuss various chemical vapor deposition technique, how we can synthesize various different surface morphology, and how we can fabricate individual nanostructure based device for sensing application. And lastly, I will briefly introduce about 2D materials, their synthesis, heterostructure device fabrication and application in plasmonic and optoelectronics device. So I will start with this 4-6 type of semiconductor. So if you see, so it has basically three main domain: germanium based, tin based, and lead based, with application in like sensor, catalysis, and energy. And this germanium based 4-6 semiconductor is special interest because it has various photophysics and optoelectrical properties, starting like darkening effect, photo bleaching effect, crystallization, doping, sensing, etc. And apart from it shows various different surface morphology nanostructure, like for germanium diselenide it can show nanobelt, step surface nanobelt, nanoflake, etc. Whereas germanium selenide it shows 2D nanosheet form. So the motivation is behind this project was like this is like 2D or 1D or quasi 1D structure. So it has basically high surface to volume ratio, of course, and with quantum confinement effect along one direction with unique density of state. So we will try to address some of the issue like synthetic and post-synthetic challenge. So how we can promote specific morphology nanostructure during synthesis. So that is common question which we can address, and also how the single device or single nanostructure based device with different surface morphology can affect the device performance. And we will also see how we can actually alter the device performance, basically photosensing, photodetector application, and how we can increase the sensitivity of this type of single nanostructure based device. So we'll try to address some of those points. So the strategy which I was following during my PhD study is shown here. So we start with the CVD synthesis of nanostructure, and then we go through various characterization technique like SEM, TEM, Raman, AFM, XRD, XPS, etc. And then we go for device fabrication to study the device performance. Here I want to highlight two techniques which I was using. One is like global laser irradiation technique, and another one is focus laser irradiation technique. So basically, if you see this image, optical image, so there is a single nano belt which is connected with two metal electrode. And if the light shine everywhere, then it's called like a global irradiation technique. Whereas the tiny light spot, if it focus at different part of the device, so that we call it like focus laser irradiation technique. And we know for this type of semiconducting and metal contact based device has various property, because this semiconducting material often give Schottky contacts with metal and sometimes also ohmic. So depending on the nature of the semiconductor, with a particular condition, like if semiconducting work function is greater than metal, then we can get for p-type semiconductor, we can get like rectifying, which is opposite for n-type. So this type of contact information also we try to get from this study. So some more about this, you can see from this focus laser beam irradiated measurement. So it is a specially resolved measurement technique, and here it is a non-destructive method to probe and locally excite the carriers, and we can get various device performance study and analyze what are the major contributing factor in the optoelectronic property. So those things we can get. Like a Schottky, whether Schottky emission takes place or not, whether there is a space charge limited conduction. As you know, the current will be square root of voltage. If there is a less conductive semiconductor, there will be like a charge accumulation, and it will sometimes give like square root of V. And sometime due to local heating, there will be thermoelectric conduction as well. And another very high issue is surface and defect state. So that also a major problem for this type of semiconductor, because that define the device performance as well. So we'll see that for semiconducting structure, how this laser beam, if has energy greater than the band gap of the semiconductor, so that time we get band-to-band excitation, and we get like intrinsic property. Whereas if the energy of the laser is below than the band gap, then we get extrinsic property like defect excited carrier generation, and there's device contribution, and the current contribute to the device. So those two also need to be noted at the start. And this is that instrument as shown by schematic. So basically the laser goes through various optical parts, and finally it focuses through the optical microscope to the sample chamber where we connect the device, and there we place the device within a controlled environment, so that we can even locally modify and locally excite under different gaseous molecules. So that also sometimes very interesting to study. So this is the experimental setup which we use. So first of all, I start with, I need to start with this synthesis. So because that is the very important thing, we need to have a very good quality semiconducting nanostructure at first. So this is the reactor chamber, as you see. So it is a horizontal tube furnace, and we use this type of various tube furnace, like horizontal tube furnace or zone split tube furnace, to synthesize this type of nanostructures. As you might know that depending on the temperature zone, this CVD system can go from like reaction limited growth to the diffusion limited growth, where the growth temperature is the higher, and there the throughput can be high. So basically we use this LPCVD is called low pressure CVD technique. and there we use for synthesizing the semiconducting nanostructures. So here is the one example as shown for zinc germanium and zinc oxide based as nanoware. So first we start with vertically aligned, this type of zinc oxide nanoware, and then we place a germanium wafer near to this nanoware sample, and then slowly we heat. So the germanium partial pressure slowly introduced to the system at a high temperature. So then what happened? Then actually if initial the germanium cell will be all around the hexagonal surface of zinc oxide. Then surface diffusion actually will take place, and there will be reaction, and it forms zinc germanium oxide, and that will get a lattice matching reactive substrate of zinc oxide. So we have this type of hybrid structure. Core is zinc oxide and zinc germanium in the cell. So it is very easy way to make a very high quality hybrid structure this way. Similarly, I also work with various other oxide or non-oxide semiconducting material as shown here, like zinc oxide, zinc germanium oxide, and later on non-oxide like germanium selenide, germanium diselenide, and nano sheet and nano belt structure, and also some 2D material like WaC2, tungsten diselenide, monolayer of MOS2, etc. So here I will briefly talk about these two, germanium selenide and germanium diselenide. So if you see these two material are very interesting because it has two highly different band gap. For germanium diselenide, it has very wide band gap like 2.7 with low conductivity, whereas germanium selenide, just if we change the composition and then we get like a low band gap and high conductive material. Also it is a like flat 2D, you can see from the bulk. We can get a bulk this type, then we can Scotch tape and we can get few layer out of this. So I listed some of the properties as you can see here. We also see some vacancy related state, so that how define their optoelectronic properties we'll see in next few slides. So for germanium diselenide, we use same CVD system, but it is a special type of CVD system, and the mechanism is called VLS, is vapor, liquid, then solid. So we start with gold thin film, then at a particular temperature it form cluster, and then this reactive gaseous species will come like germanium and selenide, and that will react with gold, and once the temperature goes to eutectic temperature of this alloy, then actually solidification and so the precipitation will take place at the interface between substrate and alloy, and then there will be vertical axis growth of this nanobit, and we can see here. And from the elemental mapping, we can see the composition like 1:2 germanium and selenide, and then the tip we have like all three element which we use gold at the substrate. So here is the condition to growth this nanobit. So after synthesizing this nanobit, we need to go for a device fabrication. So this is one technique we use to pick up single nanobit. This is also very interesting. So we need to use a manipulator with the needle at the tip, and then this tip has a very sharp edge with diameter 1 micron, and so it has very high electrostatic attraction with the nanobelt surface. So once you bring this this metal tip with the nanobelt, then it get attract and it detach from the substrate, and then we can place wherever we want. So we will take a substrate, then we place there, and then we go for lithographic, and we make pattern for depositing metal. So the details is shown here. So we take silicon dioxide substrate with then we place the nanobelt with transfer, and then coat with photoresist. Then we do laser lithography, and then we open a pattern using photolithography. Then we sputter metal. So here we use titanium gold, and then we develop with acetone. So then we get device, and this is the instrument picture photolithography. So we use this photolithography instrument and sputtering instrument. So here we use plasma enhanced sputtering of titanium and gold, and we get this type of device as shown here. So this optical image of the device which fabricated with single germanium diselenide nanobelt using single germanium diselenide nanobelt, and this is the SCM image. And from the AFM you can see it is a rectangle. It has a rectangular shape with a height of 70 nanometer and width around few micron. So once we have a device like a metal semiconductor, metal MSM type, then we go for device characterization. So here in the left panel, you can see the optical image of the device where the local focus laser beam actually excite at different part of the device, as shown position 1 nanobelt and position 2. So at 0 volt bias, if you see carefully here, the nanobelt, on the nanobelt, when we read it on the nanobelt, the current is bit low as compared to the spot position at 1 and 2. Whereas if we do the current analysis at with the sweep bias, so the scenario is different. So basically we get reverse, like position 1 is current is higher than the position 2, because position 1 and position 2 depend on the source and then where we directly give bias, and that we can explain from this band alignment. So basically at 0 volt, what happened, this semiconducting material act as a potential well for carriers. So there is very less chance to escape the photogenerated carriers from this potential well, because there is a high Schottky contacts at the gold and semiconductor at both end. So basically at 0 volt bias, there will be very little current when we irradiate at the nanobelt. But if we do forward bias or reverse bias, then the scenario will be different, because at forward bias, the metal and semiconductor, there will be low potential drop. So there will be in the carriers separation, there will be a less chance. Whereas for in the reverse bias, there is a good depletion width to create more carriers, photogenerated carriers, and that can effectively separate. So depending on the bias, we get different current as shown here. So if we do bias of this device, then the scenario will take place like this. So in the position 1, so the red line, you see the position 1 and is the here. So it is in the reverse bias direction, and there the photoregenerated carriers can readily separate, and we can have a high current. Whereas in the forward bias there is a chance also to separate the carriers, but not that effective as shown in 1. So that is the scenario when we do with local excitation. But the scenario is different if we do with broad beam irradiation as shown here. So here the light is illuminate everywhere of the device. And then if we do power dependent photocurrent study, then it takes power law like p to the power 6. So exponent factor is 0.6. So basically this value define how the defect state actually play a role in the photo-generated carriers and photogenerated current. So if it is 1, so basically there is a photogenerated carriers and it get well separated. But if the value gets below 1, that means the carriers are getting trapped in the defect or trap sites. So that is observed under global irradiation of the device. And if we do study of photocurrent with square root of V, then actually that also define that it has high Schottky barrier dominated current. Of course, that is also shown from this asymmetric non-rectifying rectifying characteristics here. So basically we have both contribution like Schottky barrier contribution and also defect traps state originated photocurrent. So some of that I will also talk in the next few slides. So next I will talk about another morphology. It is like step surface. So before we saw a very smooth surface nanobed. So it is a step surface germanium diselenide. So basically here the condition of the reaction is different. So here substrate temperature is bit low as compared to previous. And here in this low temperature region, so basically the catalysis, that when it form alloy with germanium selenide, that actually get perturbed with this vapor pressure, and it actually gives oscillating behavior. And that is also observed for other semiconducting nanostructure synthesis as well. So due to this oscillation, the steps actually come across this nanoweld surface as shown here. And then we study the optoelectrical properties because it has high steps. So definitely the traps and defect sites will be much higher here as compared to smooth surface nanoweld. So that we observe here that if we excite with near infrared light like 808 or 1064 nanometer, these two wavelength excitation give much higher current in this device. So that the energy of this excited wave laser is below than the band gap. So basically these laser excite the mid band gap energy state which are available in this nanobed. And that actually give rise and the high photoconductive gain, and we gain quite high gain. Also responsivity value is 1040 at 1064 nanometer excitation as shown here. So that we get detailed analysis from this control experiment. So here we do different environment effect on this photocurrent generation. So basically, if we see under vacuum and under pure nitrogen atmosphere, the photogenerate carriers is much higher as compared to the air atmosphere, because these defect sites which are present on the step surface are not highly engaged with oxygen molecules, oxygen or hydroxyl ion. So that's why this defect can actually effectively contribute to trap the photogenerate carriers. So once the carriers get trapped, the gain will actually, photoconductive gain will increase. That's why we are getting high current here. And power law value also actually prove that, because the value 0.052 is below than the value we got in the smooth surface nanoweld. And that we found from the theoretical analysis also, that selenium or germanium vacancy often give this type of defect state at mid band gap energy value. So that's all. So next I will I have one more structure like 2D flat surface. So we were talking about smooth surface, step surface. And then if we change the composition, we can have also 2D nanosheet like germanium selenide. And the synthesis is quite similar, but here it is synthesized without any metal catalysis. So the reaction takes place at 620, where germanium selenide crystal we use. And this crystal was vaporized, and the molecules actually get vapor here. So before there was for germanium diselenide, we use powder, and there was a carbothermal reduction. But here direct molecule can evaporate and get deposit on the specific substrate temperature as shown here. And then we get very high throughput, and we get very large high quality nanosheet as shown here. So basically argon gas flow is opposed to the flow of this molecule in this direction, and then it actually get saturated here and deposit on the substrate, which was placed at 430 to 390 degrees centigrade. And then we go for 2D, 2D material based device fabrication. So it is we need to do mechanical exfoliation of this bulk material using Scotch tape. Then we deposit on the substrate. So then we have very small. This blue blue means that it has a lower thickness. So if we see in zoom in picture here, so it has a very small germanium selenide nanosheet with a few nanometer of thickness. And then we do this type of patterning we start with silicon substrate as a backgate, then with 280 nanometer of SiO2, then we do surface treatment to remove the surface residue, and then we exfoliate sample, and finally using EBL we do source drain patterning and then metallization. So finally we get this type of chip. And then for further analysis of optoelectronic, we study the device performance. So first impression, if you get from this curve, so it has very highly asymmetric rectifying type characteristics because of high Schottky contact, which is not even. So it is uneven Schottky contacts at both points. So it gives like rectifying characteristics, and the power dependent property, so that at different power of 808 nanometer it has quite high photo current. And if we do the time analysis, like under multi-field switch on and off of the incident light, it also follow quite fast rise on, but during decay it take fast off, then it actually slow down. So there is a slow decay process as well under multiple switch on off of this incident light. So this slow decay can be due to the deep trap state which is available between this metal and semiconducting interface at the contacts. So that we study from this power law as well as from this model of Schottky contacts. So here the power law value source, and even it is the exponential value is even much below than the previous, so it is like 0.3. So that again define that there are also high gain due to this vacancy, which are from the germanium or selenium atoms in the substrate in the surface of this nanobelt, and of course there will be Schottky contacts dominated. Schottky contacts dominated mechanism. Hello.
Hello.
Hey, can you listen?
Yeah, I think somebody is sharing the screen. I think Sandeep Dey. Just a minute. Yeah, please share again.
Okay.
Yeah.
Okay. So I
now it is fine.
Few slide only because I am out of time. So I will just take few minutes to just end because I already have some problem in the initial stage. So it is so last part is on 2D material based device. So I am not going details about various application as shown here. So basically what we are doing, we also synthesize various 2D material, and we characterize using a very small optical characterization tool as shown here. So we use a very small optical tool to actually get the direct reflection and also and the transmission. So from there we extract the optical permittivity value. So it shows very high, dispersive nature of the material of this molybdenum disulfide. And later on we study with the plasmonic structure on top. So that initially that increase the scattering, as you see from this Raman scattering, and also the reflection spectra. If you see, it also changes the reflection spectra. From there you can get if you extract the information, you will get absorption. So basically here we prove that for single layer MOS2, the average absorption we can increase from 8% to 41% using plasmonic structure. So that those are the thing we do with plasmonic application for even surface enhanced Raman scattering as shown for this germanium tungsten diselenide based material. So here after gold deposition, the surface Raman scattering actually get enhanced. So that can have direct application in search sensor. So that is one type of sensing application we do with plasmonic. And there is also light emission, not only scattering, absorption, also the emission of this material can be modulated using plasmonic array. So we fabricate a monolayer MOS2 based material with a gold plasmonic array on top, and then we have shown the photoluminescence enhancing and quenching as shown here. So because of this plasmonic array, so it actually induce the electric field in the surface of the MOS2. So the enhancement get both high. The enhancement will be high in both wavelength region, in excitation wavelength as well as emission at 680. And that will directly impact to the emission process, because this plasmonic structure actually help to to populate the carriers in A and B excitonic state, and the luminescence we get from A exciton. So that way we can enhance the luminescence. And lastly, I had one work with the non-volatile memory, but as I am going out of time, so maybe I will skip this. So if you are interested, you can discuss with me later, and I can happy to give you the information. So thank you, Bhaskar, for this opportunity. So here I will end. So here is the conclusion. So I just wrote. We can see.
Yeah, thank you very much, Dr. Babluji.
Yes. Thank you very much.
So now it is question and answer session. So I request, sir, Dr. Tiwari, sir. Okay, it's okay. So if you have any queries, the questions, any questions from the participants? Please unmute your mic, and one by one we can have.
Hello.
Yes.
Yes.
Thank you for giving a nice talk. And I have one question from
Yes.
your PPT. I have found in one device you have seen the in the short key interface there is a drop, means rise and fall, so that you can
Yes.
estimate the trapping state, as you mentioned in one of the
Yes.
slides.
Yes.
So, can you tell me how exactly we can find it out the trapping state densities? So, with the trapping state density, how the curve shape it is defined?
So basically, if you analysis this, do you mean this graph?
Yes, yes, yes.
So basically, if you see the fall, so there is a fast one fall, then it has slow decay, right?
Yes.
So if you analysis with exponential decay, so definitely you can fit like two exponential function or three exponential function. So the first one you can we can talk about the direct recombination or something.
Yes, yes.
And then the slow decay, the rate will be different, and we can get different time constant.
Correct.
So that means that means those carriers, which are associated with the trap state. So those carriers have different lifetime. So
Yes.
so basically those carriers, when we'll get recombination, it will have different time response. So we can have different time constant when we fit with exponential decay. So
Yeah.
from there we can extract how the decay rate will be associated with the trap states.
Okay. That means from the structured exponential function with the lifetime, can we estimate the trap state density as what?
Yes, decay rate we can
Decay rate, yeah.
we can
With the time
extract, and yes, there are some relation you can find. Yes.
Okay. Thank you.
Thank you, Dr. Thank you, Dr. Bablu
Yes.
Mukherjee. There is one question in the chat box.
Yes.
So she is Susmita Bhattacharya. She has asked that for germanium selenide, how many layer the device which you have used
Yeah, this
for germanium selenide?
it is a few layer device, so I hope it is beyond 10 nanometer. Yes.
Okay, okay. Thank you. So any other questions from the participants? Dr. Tiwari sir, is there any questions in the chat box? YouTube?
Sir, YouTube I have not checked. I was also in meet only. Let me check.
Okay, meanwhile, if there is any questions from the participants, you can rise. You can come to unmute and you can discuss with our speaker. Okay. So, Dr. Bablu Mukherjee,
Okay.
so thank you. So, thank you very much for your, yes, thank you very much for your wonderful presentation. And it is upcoming, I mean, your work is very valid and hope it is reached to the audience. So, thank you, Dr. Bablu Mukherjee. Thank you.
Thank you. Okay, let me stop the.
Okay, so Dr. Divakar Garu?
Yes, yes.
Okay.
Bhaskar,
Yes, good morning. Yes, good morning. Good morning. Good morning. So, are you ready?
Yes, yes, I'm ready.
Okay, 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 fine. Okay, wait for a minute. So, in between, we'll introduce you with the session as per our schedule.
So by the time I will share my screen.
Yes, yes. By the time you can share your screen.
Yes.
Meanwhile, I request the participants, some of you please kindly off your mic and video also. Many participants are showing their video. Kindly off your video. Like Babu K and Sharfuddin and Damodar. Kindly off your video.
So Bhaskar Garu, is audible my voice and my
Yes,
screen
yes.
is okay?
Yes, yes. Your screen is excellent. It's fine. It's not an issue.
Okay, fine, fine. Thank you.
Sir, Karthik sir or Bhavani madam, anybody is there?
I'm here, sir. I'm inviting. No, it's
Yeah,
fine.
yeah, madam. Yes.
Okay.
Okay, madam. Go ahead. Go ahead.
Okay. Can I start?
You just, yeah, you start the session and I will introduce the speaker, madam. Okay.
Okay.
All right. Okay. Go ahead.
Okay. Welcome and good morning to our international webinar about synthesis and characterization of nanoparticles. and its novel application. So I invite Dr. K. Divakar Ucha for the next session. Now, we introduce about the sir by our colleagues, Assistant Professor Bhaskare sir. So I hand over the session to the Bhaskare sir. Sir.
Thank you, madam. So, I'd like to introduce our next speaker, Dr. V. Divakar Botsa. He's a research scientist in Optoelectronics Center at Shenzhen University, Hong Kong, Chennai. Hong Kong, China. He completed his MSc Physics from Andhra University and did his PhD on study of graphene oxide and reduced graphene oxide monolayer sheets and related nanostructured composites with cadmium sulfide and copper prepared by Lajmet route at Department of Physics in Institute of Technology, Bombay in 2009 and 2015. After his PhD, he worked for 2 years as assistant professor in University of Petroleum and Energy Studies at Dehradun. Later, he went to Shenzhen University, Hong Kong for his postdoctorate research on advanced 2D and nanostructured materials in the Department of Material Science. Currently, he is working as a research scientist in Optoelectronic Center at Shenzhen University, Hong Kong, China. So with this, a few introduction about the Dr. V. Divakar Botsa. I request him to deliver his lecture. Hand it over to Dr. Divakar Botsa.
Yes,
Thank you,
Bhaskar Garu. So very nice introduction. And first of all, I would like to thank to your team and your colleagues for giving this opportunity, for sharing my knowledge. So good morning, all of you. So today I would like to introduce my work during my PhD time and postdoc time and current situation. So mainly I worked on nanostructures like thin films. So after that I changed to nanostructures like particle, three-dimensional, 2D particles, nanorods, nanowires, like that. So I would like to introduce my work. Here this is the presentation. The title broadly I have given here: Synthesis and Characterization of Nanostructures and Composites and its Optoelectronic Applications. So this work I have done during my PhD time at IIT Bombay and postdoc time in Shenzhen University. So this is my plan of presentation: introduction of materials, where I worked, and object of present work, resultant discussion, summary, and future scope for future, what we can do with novel material. So as of you, all of you know very well-known material graphene. So we worked on graphene and graphene oxide, reduced graphene oxide, three kind of materials. Okay. So for my convenient purpose, I switch off the video. So you can hear my voice, right? Bhaskar Garu? Is okay?
Yes,
My
yes.
voice is clear?
Yes,
Okay,
clear.
So, okay. So here I would like to introduce a little bit about graphene oxide and reduced graphene oxide. So everyone know very well about graphene is a one-dimensional carbon atomic layer having the sp2 hybridization and high conductivity and high mobility, and also having this unique polar ambipolar behavior. So we can change one concentration, carrier concentration, to another carrier concentration by applying the voltage without any doping. So that is the main advantage of graphene. So we have also tried with graphene oxide and reduced graphene oxide because of by getting the monolayer, single layer monolayer from graphene. So it's very difficult. There are some direct method synthesis also available, like mechanical exfoliation from graphite and epitaxial growth from the substrate of silicon carbide, and also chemical vapor deposition. So these are the most commercialized techniques, last two. So, but here very thing is we cannot able to control the thickness at one atomic layer. So people are trying, some people are getting also, but it's very difficult and cost effective also. So there are other approaches like we can make graphene oxide easily from synthesis chemical routes. Later we can reduce graphene oxide by using some chemical reagents, reagents. Then we can get the conductivity get back. So there are methods like for making films. Graphene oxide films is very difficult. So means difficult means 1 nanometer thickness graphene oxide layers is getting difficult by using other methods like spin coating, drop casting, and SAM deposition, self-assembled monolayers like dip coating, spray coating. Because these methods very easily we can do, but problem is there are a lot of overlapping and crumpled natures we can get. So we have introduced here LB technique, Langmuir-Blazek technique. This is the very well controlled technique to control the thickness of the layers. So later, after getting the monolayers, we have followed the reduction by solid state form. So that I will discuss you later. So here I would like to discuss some synthesis LB route, how we will get the graphene oxide sheets. Then after that chemical route reduction. Then after that something new development, because LB technique also very cost effective. It's very costly affair. So not all people will get this technique. So that's why we have introduced, based on the same phenomena, we have introduced very less amount scalable to make geo monolayers, that I will discuss also. Then later I have done some work on indium selenide nanostructures also, different by using CVD, PVD, and also some hybrid structures also, sandwich structure by using MOS2 indium selenide nanoparticles. So first of all, I would like to discuss about spin synthesis. So very well-known method, like we have used some chemical route. So modified Hammers-Hoffman's method. Here we have used some chemicals like oxidizing agents, NaNO3, KMnO4, H2S4, H2O2. These are the main chemicals to oxidize the graphite, to form graphite oxide. So we can introduce some oxygen functional groups in between the graphite layer. So it can be exfoliated chemically. So without any mechanical force, chemically it will be exfoliated by introducing some oxygen functional group in between the layers. Later we can use the ultrasonication centrifugation. Then you can get the completely exfoliated graphene oxide sheets, which will be have 1 nanometer thickness. So graphene oxide mainly you can see here. So here there are a lot of oxygen functional groups. At edges, mainly carboxylic and phenol groups you can see. And at basal plane, at center of the oxygen plane, you can see hydroxyl epoxide carbonyl groups. So these are the main functional groups. It will create the insulating behavior. So while oxidizing, it will create the insulating behavior. So after reduction, we can get back the conductivity. Okay. So that is our motivation. So then we can see here. So graphene oxide. This is the graphene oxide solution, in which is soluble in water methanol 1:5 ratio. This is the obtained graphene oxide solution. So we cannot see any sediment in the bottom of the bottle. So that means it is fully exfoliated. If something is agglomerated particles are there, it can be sedimented bottom of the bottle. So that means it cannot be suitable for LB deposition. The thing is, I will tell you in the LB deposition what will be happen. We need to check whether this is good GO solution or exfoliated. By using UV visible absorption spectroscopy, we can get this graph here around 230 nanometer and small solder also 290 to 300 nanometer, which indicates pi star of carbon-carbon peak and n pi star transition of C double bond O. These are the indication of graphene oxide. So we can confirm this is the chemically exfoliated graphene oxide solution is ready for LB technique, Langmuir-Broglie technique. So before introducing this LB technique, so this is our setup, means this is the LB technique in IIT Bombay. So this is in our lab. So here you can see white color. This is the trough, Teflon made trough. You can control the pH of the trough, and this trough is full of water, milky water. Okay. So and we can see the temperature controller, pH control also. So these are the monitors we can see. And in the schematic diagram, there are two barriers in middle, one substrate and one Wilhelmine plate also there. Okay. So these substrate vertically we need to keep into the water. The water is called surface. We can call the surface this water. So on the surface of water, we can spread the as prepared graphene oxide solution. Then whatever the exfoliated sheets, it can be floating on the water. So you can see the floating of the sheets on the water. So when we apply the barriers compression, then these all sheets come closer and packed, very well packed. Then you can at the time of very packed density time, then you can slowly lift the substrate. Then substrate will be having hydrophilic nature. So obviously this graphene oxide sheets also hydrophilic nature. Because of hydrophilic nature, these sheets, graphene oxide sheets, will be transferred to substrate. So these are the standard parameters, optimized parameters. So we varied a lot of parameters. Then best conditions we obtained the sheets. So because so we can use any kind of substrate here, but the surface should be hydrophilic. For that hydrophilic substrate purpose, we can clean the substrates properly with RCA treatment. Then you can achieve the hydrophilic substrates. See, this is you can see the LB deposition of graphene oxide sheets. So here this is the curve, surface pressure versus barrier separation. See here these two barriers, you can when you are compressing the barriers, the surface pressure is building on the surface of the water, which can be measured by Wilhelmine plate. So that is in millinewton per meter. So barrier separation is, you can see 0 to 400. So when you are decreasing barrier separation, that means the surface pressure is building on the surface. So when it is increasing the surface pressure, that means all the graphene oxide sheets are come closer and close density. You can see the blue circle here around the surface pressure is 1 millinewton per meter. So this is very less surface pressure. At that time, you can lift the vertically the substrate, then you can get some isolated graphene oxide sheets individually, isolatedly. If you increase the surface pressure, some more close barrier compression you can do, then you can get the surface pressure more. Then by increasing surface pressure, you can see 2 to 3 millinewton per meter. The sheets also very close, and while increasing surface pressure, it's very closely dense and overlapping at 15 to 20 millinewton per meter. Okay, so this is the way we can deposit at depends on the applications. If you want closely dense packed sheets, you can get it at increasing the surface pressure, and if you want isolated sheets, you can get at lower surface pressure. So this is the way you can control the density of the sheets by using Langmuir-Broglie technique. So this is the typical AFM image. You can see the cross section is about 1.3 nanometers. So it is considerably 1 nanometer around. So it is well defined, and the sheet also very flat and no wrinkles, no overlapping. We can see at optimized conditions. So this kind of sheets is very useful for optoelectronic applications, some device fabrications. Okay, so later, so once we get the GO, very well defined GO, then we can go for reduction. So here, this is the reduction method we have set up for hydrogen vapor treatment and also thermal treatment. So here hydrogen vapor, we can expose to hydrogen vapor. The samples are exposed to hydrogen vapor at 45 degrees Celsius, around 18 hours to 24 hours you can increase. And heat treatment you can also do around 400 degrees Celsius. At 400 degrees Celsius, 3 hours, 6 hours you can do. I have tried 3 hours and as well as 6 hours. So for comparison how the conductivity is improving. So this is the after morphological study for graphene oxide and reduced graphene oxide at different stages. So these are the AFM images, first three. So one is graphene oxide, another one, two, R1, RGO1 and RGO2. These are two reduced graphene oxide as well as SCM also you can see here. So by seeing this morphological study, so there is no morphological variation during reduction treatment. So that means our reduction is will not damage our morphology of the sheets. Okay. So that means it will be very useful for further process. So this is the thing we can observe from here. And also we have observed the thickness is varying. So the thickness from graphene oxide to reduced graphene oxide is decreasing about 0.1 to 0.5. This much of range you can see the variation. So that means oxygen functional groups are completely removing, so that the thickness of the sheet is decreasing. Ideal graphene thickness is 0.3 nanometer, 3-4 nanometer. So, but experimentally we cannot get 1 nanometer is the experimentally acceptable value. So we have done some XPS study and Raman study also for observing the how good the reduction and how good the conductivity purpose. So here you can see GO, RGO1, RGO2 XPS data. So from this data you can see the many of the functional groups. Oxygen functional group in GO you can see around sp2 is 5.2. sp2 is the main function for graphene, so it should be very high. So this is the for pure graphene it should be 100. So because here there are 100 of many of oxygen functional groups are there. That's why it is 42. Then after reduction it goes to 70. So the ratio of oxygen to carbon also it is decreasing. That means oxygen functional groups can be removed by this hydrogen treatment followed by heat treatment. So you can see the 2 to 3% carboxylic acid groups at periphery region we can remove during this reduction, and also hydroxyl and epoxide groups also we can remove, so at interior behavior of the sheets. Okay. So here this is the Raman study. I think some image is not clear. Okay, something disturbed here. Here this is the Raman. Here I mentioned only G-peak. G-peak is the main indication of the graphene and the reduced graphene purpose. 2D peak is not visible because this is the not graphene. This is the graphene oxide, reduced graphene oxide. Here this is the G-peak is indication of graphene. So generally it will be for graphene 1585 centimeters. That is the peak range. In case of graphene, it will be 1600 to 1598. That much range you can get. And when it is during the reduction, you will get the redshift up to 1593, 90 also depends on your how good your reduction. So we can see from these peaks also, peak positions, we can say the reduction is taken place. So this is the consistent with XPS results also from GO to RGO. And also this is the most important, we have did this EFM technique. So to know the how good conductivity compared to GO and RGO. So EFM technique is basically is one of the mode in AFM. Okay, so this AFM is the secondary image, like phase, sometimes voltage also we can collect. This is the AFM. So generally in AFM we can do at atomic with atomic forces, means the tapping mode. In tapping mode, the tip will be contact to sample. But while while doing electrostatic force microscopy, so the tip will be lifted to up to 100 nanometer. 10 nanometer, up to 10 nanometer. In that lift mode, so atomic forces will be disappear and electrostatic forces will be formed between the conducting tip and sample. This is the like same as like EFM technique. So here we need to apply the voltage so to the sample or tip. So then we can get the phase image also as well as. So this is the phase formula. So here Q is the quality factor, K is the spring force constant. These are the depends on the tip, what kind of tip you are using, and VT and Vs is the sample bias and tip biases, and C is the secondary derivative of the capacitance between the tip and sample. So from while doing this experiment, we can observe this kind of data. So this is the first one, graphene oxide, then RGO. The second two is vertically. Those are the RGO2. I think is shifted these values. I don't know when it is. Sorry for that. So GO is the first two images. AFM image, the corresponding second line first one is corresponding EFM image. The second next two vertically is RGO1 and RGO2. The corresponding EFM images are bottom. Okay, here you can see when you are doing GO EFM image, there is very little dark compared to RGO1 and RGO2. You can see the RGO1 and RGO2 EFM images, so very darker. That means the contrast, the phase is increasing lot in case of RGO1 and RGO2 compared to GO. So that means the conductivity, when the conductivity is increasing, the contrast is increasing because of contrast increasing due to the conductivity, because the surface charges will be accumulated when you are applying the sample bias or tip bias. It's very easily get the charged. So that's why phase will be appear very drastically compared to GO. So in this ways, after doing several positions, several samples, you can record some of the things like this. So phase shift versus height, the lift height, sample height between the sample surface to tip distance. You can see these two curves, RGO1 and RGO2, because the phase shift you can get only conducting samples only, so not GO. And also for GO, you can second image you can see here. So phase shift versus tip bias. So this is the, so you can see the two graphs here. This is the one, you can see the more curvy nature having RGO2 and less curvy nature is having GO. So that means this is the, and also vertex point 27 millivolt, that is not exactly at zero, it is shifted towards positive direction. That means this vertex point also you can based on this vertex point you can judge what kind of material this one, either n-type material or positive material, or n-type material or positive material, p-type material, you can judge based on this positive value, and this is the value indicates the p-type behavior of the RGO1 and RGO2. So this is the way we can conclude based on using EFM technique. You can conclude the comparison study between insulating and non-insulating means conductors, and also type of conductor, what kind of polarities are existing in the samples you can judge also, because most of the people are doing composites, some insulating, semiconductors, metal, these are things. EFM is the good technique to identify the conducting nature between two kind of samples. So easily you can judge comparative study. So another way, sorry, this is the not this one. So this is the one here. This is the electrical measurements. Okay, so this is the electrical measures also we have carried out on the GO and RGO study. This is the standard lithography pattern how we are doing. So this is the standard steps for lithography, and we have used both shadow mask optical lithography and also electron beam lithography. So this is the one also. FET, by using FET grid, also you can very huge number of samples you can do very fastly, because lithography will take time also. So based on by using a grid structure also, you can make the contacts on isolated graphene oxide sheets or reducing graphene oxide sheets. So by using these techniques, you can get the current IV characteristics and transfer characteristics. Okay, so you can see the insulating behavior to conducting behavior. So graphene and RGO, and also here ambipolar structure. This is around minus VG. Negative side is increasing the p-type behavior. So more prominent p-type behavior RGO1 and RGO2 compared to n-type. So this is the one. So ambipolar, but not equal concentration in case of RGO, not like graphene. So this is the one kind of evidence. So these are for how good your reduction, and these results are consisting with EFM results. And also we have published some papers on this based on this data. Okay, so we can conclude from this data, we can conclude some isolated geosets we can make it, and which are size in 10 to 15 microns, and also EFM XPS Raman study we can do to confirm the reduction stages, and electrical properties we can do based on FET structures. Then further we can do the sensing applications also by using these FET structures. So here this is one technique, so which we published also in Indian patent. So this is the modified LB technique. So this is the very simple technique. So generally LB technique is cost like around 30 lakhs to 20 lakhs to 30 lakhs will be there, depends on the parameters or feasibilities. And here we can do some modification. We can use the same phenomena but without any power supply, and just simple 300 rupees cost of beaker and some pipe and some small rod. We have make it by using 300 rupees. Then you can get same quality of the films, graphene oxide films, what you will get from LB technique. So this is the only useful for graphene oxide, not for any other amphiphilic molecules. So only graphene oxide films you can make easily, very low cost and without any power supply, and also the quality is as same as LB technique. So this is the beaker you can see here. So the bottom is draining tube is there, the millicube water you can fill, and later you can substrate you can hang vertically. Then after spreading graphene oxide solution on the surface of water, so after 1-2 hours we can leave for evaporating the solvents from the surface. Later you can slowly drain the water from bottom. So it is depends how quality, how much quantity you are depositing on the surface of water, you will get the density, that much of density you will get. So you can see the sheets, because substrate is also hydrophilic and sheets also very hydrophilic, so that's why easily it can be attached. So very slowly we can drain the water, and you will get the homogeneous sheets that you can see here, the parameters. And also you can vary the surface pressure also by introducing the volume of the graphene oxide solution. So here these are the parameters for this. Okay, so what kind of parameters can change in modified Langmuir-Blazet technique? So this is the one. So compared to of the LB technique, we can see the draining. Here the subspace will be drained, and here substrate will be vertically lifted, and the uniform deposition, control, surface density, everything will be same, and elaborate high cost in case of LB technique, and modified LB technique is simple and low cost. And results you can see here by using MLB technique. So this is the results. So you can control the density of the sheets, and very flat and united. And after that we have done standard reduction process what we did for LB technique, Then you can see the Raman and electrical data also by using this technique. That means the films everywhere is what we got from LB technique. Modified LB technique also gives the same results. Then we have published this one in Indian patent and as well as other publications also. And also this technique can be used for cadmium or metal, any metal salts composites with GO. So what you will do here, so by introducing water, pure milky water, you can introduce some cadmium chloride, zinc chloride, copper chloride, any kind of salt, metal salts we can introduce in the surface. Then you can just change the pH. pH we have to change because by using some buffer solvents. Buffer solvents you can change, you can around 6.5. Generally it will be 5.5 you will get, but 6.5 and higher pH where you will go higher pH of surface water, then the ions will be decomposed. Means ion can be separated, Cd plus Cl2 minus, like that. This Cd2 plus, copper 2 plus, zinc 2 plus, these metal ions can be easily attract or attached to graphene oxide sheets, because graphene oxide sheets also having some carboxylic groups. Those carboxylic groups at higher pH it will be ionized. So COOH becomes COO minus. Then Cd2 plus will be attached, or Cu2 plus or zinc 2 plus. Any kind of metals you can introduce in the surface water. Then you will get the composite material, which can be very useful for sensing applications and other optoelectronic devices. So this is the advantage of graphene oxide and reduced graphene oxide. So you can see the results. I'm sorry, these are the modified when you here this is the Cd2 plus graphene oxide CD. When I introduce Cd2 plus means CdCl2 so salt I introduce with different concentration, 10 power of minus 2 molar, 10 power of minus 4, 10 power of minus 6. Okay, then after introducing I do the sulfidation, it becomes CDS. CD becomes CDS during the sulfidation. So you can see the H2S gas exposure. So 15 minutes, 2 minutes, 2 hours you can do. Then you can able to see the particles. These are all AFM measures on the sheet, not on any kind of other substrate. Here you cannot able to see clearly sheet, but these are the at a high resolution AFM images at sheets, because when we are going for microns range of graphene oxide, you cannot able to see the nanoparticles. That means we should go at higher resolution AFM. So that there you can see clearly these nanoparticles. So here CDS with graphene oxide you can able to see. So and also for confirmation XPS and HER-TEM also you can see. So here from XPS data, CD3D, CD3D, this the core of CD structure. You can see the two peaks in case of GOCD 405.9 and also 412 in case of after sulfidation CDS the shift, small shift 405 you observe 0.5 variation shift. That shift also indication of formation of CDS, the binding energy. And also here the sulfur peak is disappear in GOCD before sulfidation. Of course after sulfidation you can see clearly sulfur peak 160 around the peak. So these are the two experiments. So you can see the CDS formation and also final confirmation. You can do the HRTM. Here first image of HRTM. This is the clearly you can see GOCD sheet, graphene sheet here, and also that is a hexagonal SAD pattern. There you can confirm this is the graphene. And also in case of HRTM images, you can able to see small particles in the range of size 12 nanometer. And also CDS, this HRTM, you can see the patterns by using HRTM. In Raman's we have done, there is no change in G peak. That means CDS interpretation of CDS will not affect any G peak position. So that is the we concluded. Here I'm not showing the data, Raman data. And the same way you can do the GO copper also. GO copper, we can introduce copper chloride solution in the surface, and you can attach some, you can change the pH of the solution. Then you can get some uptake of copper metal into the graphene sheets. And then you can do the some oxidation also, as well as heat treatment in vacuum also you can do. I have done 200, 300, 600, and you can see without treatment, without heat treatment, before heat treatment, you cannot see any sheet. Okay, so but in case of in case of heat treatment, just a minute. So in case of heat treatment, so at 400 and 600 you can see clearly the particles, the range of the size of the particles about 60 nanometer, and in case of 600 degrees Celsius about 100 nanometers. Whereas 200 degrees Celsius, we haven't seen any kind of particles. Maybe take this is not optimized parameter for getting copper nanoparticles. Then after that we did XPS study on these different treatments particles. Then we can see here the copper, by introducing copper at heat treatment also, simultaneously reduction also happening. So you can see here the ratio sp2 carbon ratio, sp2 hybridization carbon ratio here 64 to 73 you can increase. This is sp2 hybridization is increased. That means during heat treatment graphene become RGO and as well as copper. So RGO with copper, it is a very good material for optical sensing applications. And here you can see the HR team on these samples also. Before heat treatment, you cannot see small clusters or some agglomerated particles. It maybe in oxide formation. Later, after treatment, you can see the very big particles in the size of 23 nanometer and sad patterns you can see before heat treatment. Okay, before heat treatment is a ring structure, and yes, images are not clear. Something changed. Sorry, so I cannot get back now. So from this way, this is the conclusion for this MLB technique, modified Langmuir logic technique. Is the simple technique, and we can do at your room itself. No clean room is required. In your at home itself, you can do the this kind of experiments, deposition experiments. No need to go to lab. So this is a very simple technique. You just buy the beaker, and liquid water is necessary, and some other chemicals. So you can do the experiments at your home itself. And characterization, of course, characterization purpose, you need to go back to lab. So and also we have done some electrical measurements on this, and this technique is very suitable for graphene oxide based semiconductor composites like GO CDS, GO copper, and GO zinc also we have done, not shown here data. So later during my postdoc, I shifted to some other 2D materials, some like advanced after graphene. There are a lot of 2D materials introduced by other researchers. So one of the material, 2D material, non-transition materials, TMD materials, and non-transition materials also, like MOH2 is the TMD material, and indium selenide is the non-transition material. So here this is the indium selenide. So here actually I want to do indium selenide sheets, but by using the PVD and CVD techniques, but we cannot get, because very complex material this is, and very useful for non-voltaic phase change memory and optoelectronics applications purpose and solar cell solar energy harvesting purpose also. These 3 and 6 semiconductor composing materials. So this indium selenide mainly existing in different kind of stoichiometric ratios, like indium selenide IN2SE3, IN3SE4. These are the different composites. It depends on the deposition parameters, and also each stoichiometric ratios also having different kind of phases, like alpha, beta, gamma. These are the different kind of very complex material. So, but the results are very nice and very changing drastically. Depends on the parameters, deposition parameters that we can see here. So here, this is the I have used PVD technique, physical vapor deposition. Here, just we need to heat it at center of the furnace, and we can place the substrate position horizontally or vertically. We can cap also. So depends on the distance, sample distance, temperature, glass flow rate, direction, everything will be changed, and at optimized condition you will get the sheets as well as some nano structures also. Here we have used IN2SE3 powder, and the motivation we need to get the sheets. Okay, but I didn't get any sheets. I got some different kind of structures. So at different parameter variation, with different parameter variation. So I have deposited these nano composites at 650, 750 and 950, 850. These are the things. So you can see clearly SEM images morphological study around the 650. You can see very nice particles, but random, irregular nanoparticles. The size variations are irregular. And in case of 750, there are pyramid and square, cubic type of particles. You can see about 100 nanometer, 130 nanometer. Okay, and in case of 850, you can see very spherical kind of particles, very nice spherical structure particles with diameter of 500 nanometer particles. You can see in case of 950, you can get the 3D structures like nano rods. These are the things. These are the high temperatures because of the at high temperature the sulfur can become very active. So due to the sulfur low melting point, this is very changing the structures very drastically from 50 degrees Celsius. Also the structures are also changing. So I want to check this thermal properties before making any fabrication. We need to check thermal properties. For that, before the primary characteristics like XPS, I have done what happened is indium selenide is whether it is in indium selenide format or something other format like IN2SE3, IN3SE4, like that. So here you can see 650 and 750 and 850, 950. When the temperature is going up, the indium concentration, indium material is degrading, and selenium percentage is very increasing. So this is the indication of stoichiometric ratio of indium selenide. It depends on the growth temperature. It can be lead formation of different structures. So, and still it is indium selenide format. The structure is still uncertainty whether it is in which form. That for that we can study Raman. So from the Raman study you can conclude from Raman we cannot get at 650 any peak. In case of 750 you can get the peak around 130 centimeter inverse. In case of 850 you will get 2 peaks, and 950 based on this literature and this structure analysis. So we can find at different temperatures the indium selenide existing in different phases like gamma and alpha, beta, alpha, gamma mixed also. So this is the we observed chain structure at a higher temperature. Selenium as formed as a chain structure of trigonal selenium crystals. That's why it becomes rod. So these are the Raman study. We can identify the different crystalline structures of indium selenide. And also we tried for thermal properties. thermal properties by using Raman study. So these are the thermal conductivity we can calculate from by using this formula. So here the temperature, you can vary the temperature from room temperature to high temperature and record the peak positions. In one particular peak position you can record. Then slope you can get that is called the coefficient, thermal coefficient, and also you can record the data from various laser power you can vary and record the peak positions, and you will get the power coefficient. Based on these coefficients you can calculate the thermal conductivity of the nanomaterials or thin films. Any kind of thin films also means it should be very uniform nanoparticles, so very high density, it should be like thin film. Then only you can use this formula for that. So based on using this formula you can calculate the thermal conductivity when it shows the values based on this data by increasing the conductive growth temperature. The thermal conductivity is decreasing. So high thermal conductivity also very useful for some applications, and low thermal conductivity also very useful. So based on this study you can use what kind of structures in what kind of application device structures, so that you can do it. And these are the summary conclusions, and we published this data in other journal Journal of Alloys and Compounds. So these are the summary and conclusion, I think. So Bhaskar, I have time, right? Can I go further? Hello? Hello?
Excuse me, sir. May I ask one question?
Yeah, just wait. I haven't completed. Yeah, just wait. Yeah, so I just want to know the time. Sorry. Oh, structures are clear. Yeah, and also I tried for, yeah, hello?
Hello, Divakar sir. So I am Professor Bhavan Narayana.
Sir,
So, first of all, I would like to congratulate you to develop a very simple and economical technique of modified LB technique for growing the films. And just I wanted to know from where this XPS studies you did?
From IIT Bombay.
IIT?
IIT Bombay.
Okay, good. So, very nice. But FTR is it for the surface, Raman, surface Raman studies? Is it surface Raman or conventional Raman?
Conventional Raman, sir.
Conventional Raman. Your layers are so thin, could you get the real signal for
yeah. So, but we have used high power and some lenses we modified, sir. So you are right, exactly. First initially we didn't get any signal. So later we started after several experiments, changing lenses, high power, everything. Then we got the signal. That one. Yes, sir.
Very good.
Sir, small interruption. Hello.
Yes. Yes, sir.
Am I audible?
Yeah.
Yeah, you can complete the session. Maybe you may have some. You have a time, so you can take 5 more minutes.
Yeah. Thank you. So I will complete that.
Yes. Okay.
So, and another one is by using seed layer effect, how the structures are modifying. Now we have seen different kind of indium selenide nanostructures like particles, cubical and spherical and nanorods, flavors, these kind of structures without any seed layer. Now I want to introduce some seed layer as MOH2 seed layer prepared by chemical route, chemical vapor deposition. These are the setup. So here as prepared MOH2 sample on SaO2, so we can keep on the top of the board where the powder, indium selenide powder is there. Then you can do the as usual PVD on MOH2 seed layer SaO2 substrate. So you can see the structure how it is changing. So the same experiments we have done this 650 and 750, 850, and with seed layer effect. The seed layer effect, see around 750, the structures are completely changed. Something is something like necklace, chain type, necklace type structures we can able to see, like nanowires. In between particles are there again nanowires. So at 750 we did some optimization around the flow ramp up, temperature ramping up 50 degrees Celsius per minute and 25 degrees Celsius per minute and 45. But around 20 to 30 degrees Celsius per minute, that the growth temperature ramp up speed also one of the crucial parameter in this making structures, this nano wire structures, necklace type of nano structures. Then we did a lot of time variation deposition, like 15 minutes deposition, 30 minutes, 60 minutes. So to identify what is going on. So you can see in case of 15 minutes deposition, you can see very small tiles or something is started to grow. So you can see the particles. There is some small tiles also open up, and in case of 30 minutes deposition, you see the nanoparticles are arranged side by side, and in between you can see clearly. There is small wire is also there in between. In between every 2-3 group of particles, you can see small wire. So these wires also growing in between the particles, and later for longer deposition, around 1 hour or 60 minutes, you can see very nice structures like necklace type or chain type structures you can see. So these are the for longer duration, you can see the morphology. I'm sorry, this format is missing. So based on this, we have done, XPS is missing. I'm sorry for this. So let me go for HRTM. And here we did the particle and as well as that wire we cut in the FFT analysis we have done, particle as well as wire also, in what structure it is having. So HRTM analysis in case of particle, it is like indium selenide also existing in single crystal. Indium selenide like IN4SE3 orthorhombic phase also. It is matching with orthorhombic phase, that single particle. And whereas in wire case, that FFT analysis gives the information about a beta structure of hexagonal structure with lattice constant 3.3 angstroms. So these are the structure analysis we can do, and based on that we can go for applications and these things. And also this is the summary of this work. Also we have published seed layer effect. Sorry, some slides are missing and displacement. And these are the morphology wise we can analysis on SaO2 substrate, and substrate also very crucial parameter, one of the parameter. You can change the silicon, SaO2 and other substrates, the structures will be different. So that we observed also. And based on these structures we can go for other novel materials also. So this is the things we can do. And also we have done some hybrid structures also. I don't have that much time, so we can stop here now. So thank you.
Yeah, thank you very much, Dr. Divakar Garu, for your wonderful presentation. So it's very useful for the young researchers, and
Yes.
now it is open for the question and answer session.
Hello.
Yes.
Thank you for the nice talk, Dr. Divakar. So I have
Yes, thank you.
two queries. One is like your LB technique, what is the cost effective compared to CVD? And the second question is like mostly the graphene sheets are in a large area. It is very difficult to get it. The till now
Yes.
the reported graphene sheets like by using the hot wire CVD, we can
Yes.
put it in
Yes.
a large area. Compared to that, in your LB technique, what is the maximum area of the graphene sheet you can get it from your technique?
Okay. Okay. So actually, can I answer your question? Yeah. Hello. Yeah. So first one is the cost effect. In case of LB technique, it's about 20 lakhs to 30 lakhs. That and also we need to maintain every time, and the clean room also necessary for that maintaining that LB technique. And but you can go for a modified Langmuir logic technique. You can use very easily that technique anywhere. So that is the just 300 rupees or 500 rupees you can expand, and you can do that same kind of experiments. And you can see my papers there. I mentioned clearly how to operate everything, so you can go through that. And in case of size, what you ask, that is right exactly. In commercial purpose, by using CVD, you can get very large sheets. Commercially, company wise, they are using, but very not in 1 nanometer thickness. It's very difficult to get 1 nanometer thickness by CVD. But in case of chemical roots, we will get up to 100 microns, up to 100 microns. So up to publication, not for these chemical roots mostly not commercial, just for research purpose we can do, and also some using some chemical devices like sensors, some composite sensors, those you can do it by using these things. But very large scale means maximum we can update, we can get up to microns, 100 microns range sheet you can get. Thickness is very countered, very well countered in case of chemical roots. So is it clear my answer? I think so.
Yes.
Hello.
Thank you. Yes. Yes. Now I got it. Thank you.
Good
Thank
morning,
you for
sir.
giving it.
Yeah.
Good morning, sir. Devakar,
Very
sir.
good
This is
morning.
Chandrasekhar.
Yeah.
I had a small doubt, sir. Actually, for graphene oxide, XRD peak around 10 to 15. But the same graphene oxide.
XRD?
Yes, XRD peak.
Okay.
Graphene oxide composite, in graphene oxide composite, there is no and disappearing of the XRD peak. What is the reason?
Yes.
That is one question.
Yeah. Actually, yeah.
Sir.
Tell me. Sorry.
Second question. In other composites also, nano composites also, shifting of the XRD peak. For example, if a zinc having the XRD peak at around 30 to 35, when it is mixing and preparing composite, zinc, iron, or zinc other compounds, shifting of XRD, that is also have small doubts why shifting the XRD peak. The third one, GO, graphene oxide and RGO. What is the difference between GO and RGO? In most of the cases, we are using RGO in different applications. Why not GO, graphene oxide? And graphene oxide is useful for energy applications?
Yeah.
These are my small doubts.
Yeah. So first of all, I want to know the thickness. Actually, pure graphene case like 100. Below 10 nanometer thickness of graphene oxide or graphite oxide, we will not get proper XRD peak. Actually, XRD peak is required from layers of atomic layer. So then only we can get the XRD from reflected bottom of the reflected rays. Then you can get the XRD patterns. But in case of your composites, it is randomly. It is the sheets. Everything will be crumpled. Means it may be when you are doing like not layer form. It is like composite form, means it is curled and wrinkles. So we cannot get proper arrangement of atoms in the graphite particles. Graphite. So there are a lot of sp3 hybridization carbon atoms in case of graphite or graphene oxide case. If you take the pure graphite, then you will get the XRD. Okay, because those atoms are very arranged very systematically. In case of graphene oxide, there is no atoms systematically arranged because of the existing of oxygen functional groups. So that may reason for both the first two answers.
Okay. Okay.
And I never did XRD because most of the work I did based on the 1 or 2 layers up to that level only. So that's why I never expected XRD from that nano range 2D layers. And in case of the third question is GO or GO. So the main difference is GO is the highly insulated. It becomes like insulating material, high band gap, because by introducing the oxide groups, epoxy, carboxylic group, phenol groups like that. And in case of RGO, we can reduce by reducing agents like DMF solvent. This is one of the reducing agent, and also hydrogen wafers or hydrogen solution. So you can attach these solvents to reducing the graphene oxide. Then you will get back conductivity. Not 100% you will not get conductivity, but moderate conductivity you will get compared to GO, not like graphene. That is the two difference you can see. Yes, any more?
No, sir. Thank you, sir. Thank you for your answers.
Dr. Tiwari, sir. Dr. Tiwari, sir. Small interruptions. Dr. Tiwari, sir, is there?
I have seen some questions in the messages.
Yes, yes.
Yeah, what
exactly. Actually, there are some questions. There are some questions from the YouTube. I have pasted there. I have pasted in the chat box. So you please go through, sir.
Yeah.
So in the chat box there is a question like from Susmita Bhattacharya.
Yeah, I'm going through.
Okay. Yeah, please. Okay.
At IN2SC3 films at 950, some are making films also, but I never see. But I have seen one nano ACS nano paper. Our Indian only he published. She published her name is Balakrishnam something. So based on her name, her paper only I have done this work, but I haven't get any kind of sheets. But it depends on the PVD setup, and there somewhere leakage is there. Then a very sensitive instrument. Actually, based on my experience, PVD is very simple. Looks like it's very simple. That but is very sensitive to all parameters, even time, flow rate, and oxygen. But the thing is, we don't have the flow meter, organ flow meter. That is maybe one of the reason I didn't get the films, but I got these structures. If everything is controlled like flow meter and temperature controller, everything, so it maybe you will get the films also. That is my answer. And what was the substrate used for deposition of graphene oxide? So SaO2 and silicon, titanium, all kind of metals we have used, because metals are mostly hydrophilic, and SaO2 silicon and SaO2 substrates also partially hydrophilic, but you can get fully hydrophilic means zero contact angle, means contact angle deposition, contact angle measurements if you do, so the drop can be very flat. So in that way, silicon SaO2 also you can use. Most of the metal kind of substrates also you can use, but preferably very smooth substrates. Even quartz also you can do, glass also you can do. Depends on your applications. If you want to do semiconductor application, you can go for SaO2 silicon, and if you want to go for optical purpose, then quartz, glass, transparent any conductors also you can use. And you can use I have done some work on zinc oxide substrate also. I have done zinc oxide nanoparticles on glass substrate by using RF sputtering. Then we have deposited very nicely graphene oxide sheets. That also we have published. You can see my Google citation papers also. That maybe help you. And what was the temperature variation during? So it's the room temperature. At room temperature itself, you can do the deposition, graphene deposition. there is no need any power supply and no requirement of any temperature also. So just room temperature itself you can do the deposition. So MOS2 we have done deposition at around 830 degrees Celsius by using CVD technique. And that may be that one the things. Useful device application continue filling needed. Yeah, any temperature, yes, depends on the MOS also is the temperature dependent growth. So you can get mono layers and multi layers and a few structural variations also. Even get even one of my lab mate, he got the vertical sheets, vertical nano sheets, MOS2. And the position, the structures also depends on the substrate angle. You can change the substrate angle and you will get the many different novel structures. So you can work on novel structures, depends on the applications. You can find various applications. You can do some publications also on that. So anything?
Yeah, I think all the questions have been covered, Dr. Divakar Botsa garu.
Yeah.
So any question, any one or two question from participants? Otherwise, we can close this talk. Any? Because we are running time.
Yeah.
Okay. So thank you, Dr. Divakar Botsa garu for a wonderful session.
Yeah, thank you very much for this opportunity. So hope we will meet again several conferences like this. Be happy.
Yeah. Sure. Thank you. Yeah. Sure. So thank you very much. So now the session talk 2 is closed in the day 2 session. So the next session will start in a short while. So, Sir Bhagwan sir.
Yes, I am here.
Sir, shall we give some 5 minutes break and then we'll start, so that it will be by that time you can share the screen and all. Some 5 minutes break.
Right. We can adjust ourselves. I don't.
Sir.
So.
Okay. Because some of the participants are requesting for a break, so I just want to convey, sir.
So in between we can settle down all the technical issues, if at all.
Yes. Okay, sir. You please share the screen by the while.
Yes, we are doing it.
So the next talk in the day 2, that is by our ex-director, Professor G. Bhagwan garu. It will be after 5 minutes. So thank you all. And in meanwhile, there is a notice that already the feedback link is which posted in the chat box for the 2 talks in this day 2 webinar series. So I request the participants to go through that. Thank you.
So Bhaskar garu,
sir,
my screen is visible?
No, sir, not yet.
Oh, okay. You have to, I think, give the. పొద్దున్నైతే చాలా సేపు 2-3 సార్లు చేశాను. మరి నువ్వు వచ్చేసింది మళ్ళా చెప్తాను. హలో
సార్, I'm in live.
ఓకే.
మీరు ప్రజెంట్ స్క్రీన్ ఇవ్వండి సార్. ప్రజెంట్ స్క్రీన్ ఉంటుంది.
ఓకే, ప్రజెంట్ స్క్రీన్ ఉంది. సో We did already that present screen already there. My PPT is
Okay.
there. Is it visible or not? PPT.
No, sir. Okay. It's not visible, sir. I'll just see, go through your name. Sir, is it with your name only, sir?
Yes, it is. Today it is with my name only. My picture also. This is the what you could say.
Actually, you are talking, right now you are talking, that is
Okay.
with your photo already is there, no, sir? Actually, that one. I'm
Okay.
finding the way. We'll just see that.
So, he can look
So actually, in the people's name, only one name is there, sir. That is yours. Only one name, not the PPT, sir.
No, we are getting other names also. We are able to see the
No, sir.
73
Yes, sir.
people.
Yeah. 73 people are there, sir. Among 73, only your name have only one. Okay.
Yeah, only one Gmail ID. Last time we used my PC, so that was the issue. But anyways, I'll try with another computer, but there is some other issue I feel this time. So okay, 5 minutes slow, then I'll just see what we can do. Uh, can you see my screen, sir? Okay. Thank you, Tashi.
Sir, now it is fine, sir. Excuse me, sir. Now it is appearing.
Okay, sir. Okay, thank you.
సార్ గుడ్ మార్నింగ్ సార్. సార్ మైక్ ఆఫ్ లో ఉంది సార్ మీది. అవును, ఐ మీన్ గుడ్ మార్నింగ్ టు డాక్టర్ సుబ్రహ్మణ్యం నాయుడు సార్. సార్ యువర్ మైక్ ఈజ్ ఇన్ ఆఫ్. ఒకసారి అన్మ్యూట్కి వచ్చి మాట్లాడండి సార్.
Yeah, just a second, sir. We are just resolving some technical issue. We'll just go back.
Yeah, it's okay, madam. I am talking to other one of my teacher in between.
Yeah, okay.
సార్ మీది మైక్ ఆఫ్ లో ఉంది సార్, అన్మ్యూట్ లో ఉంది, రెడ్ కలర్ లో. రెడ్ కలర్ లో ఉన్నదాన్ని మీరు ఫస్ట్ది లెఫ్ట్ సైడ్ రెడ్ కలర్ లో ఉంటుంది మైక్ సింబల్ తో, అది ఆన్ లో ఉండాలి సార్. అది మీరు ఆన్ చేస్తే వినపడుతుంది సార్.
Hello?
Yes, sir. Now it is perfectly all right, sir.
Okay, good. So, whenever you tell, I will start. Today, I think there is no need of introduction of mine.
Yes.
Yesterday already you have given.
Yes.
We can save 2 minutes at least.
Sure, sir. So we'll start, sir. Are you ready, sir?
Yes. I am ready.
Okay.
Just say one line. Just.
Yes, sure, sir. Actually, Dr. Tiwari will take the lead, sir. Okay. Dr. Tiwari garu.
Carry on.
Sir. Good morning.
Good morning, Bhaskar. Carry on.
Right, sir. Thank you.
Right.
Sir.
All the best.
Right, sir.
Okay.
Dr. Tiwari garu, Dr. Bhargavan Tiwari. Okay, it's okay then. So, good morning, one and all. So, in these 2 days, we had 2 important talks yesterday, and 2 more important talks has been covered today. So, in this second day, that is talk 5. Again, the former, the beloved director of the RGUKT-R.K.Valley, G. Bhagavan Narayan garu, is presenting his talk, that is talk 5, that is characterization of nano crystals, particles, thin films and their structures. So I request Professor G. Bhagavan Narayan garu to deliver his lecture. Sir, over to you, sir.
Okay, thank you, Mr. Bhaskar garu. Thank you so much for your short introduction. And again, I would like to thank the organizers and the authorities of the RGUKT to give me a chance to grace this great occasion. And it is my privilege to do anything for do something for the RKV branch of RGUKT, because I served there for more than 2 years as a director. So it is always a pleasure to do anything from this branch. I'm once again thankful for giving me this opportunity. So yesterday we have discussed about various methods to synthesize the nanocrystallites or particles or thin films and their structures. Today I will try to discuss various characterization techniques to characterize all these varieties of nanostructures. And okay, with this little introduction, I would like to start. Okay, yesterday I have spoken about the RGUKT, and today I would like to say a few words about National Physical Laboratory, where I served that this institute for more than 32 years as a scientist, and I superannuated in 2015 as a chief scientist and also as a head of the characterization division, sophisticated analytical characterization division. So I would like to speak a little bit about this. It is a privilege and honor for me to talk about the institutes or labs where I served actually. So this is the front view of the National Physical Laboratory. It is situated in New Delhi, and it is one of the premier and earliest national laboratories set up under the Council of Scientific and Industrial Research. And late Sri Jawaharlal Nehru laid the foundation stone of NPL on 4th January. That means it is even just before the independence actually. So that means our leaders have a great vision about science and technology, and they know without the progress in the science and technology, our country cannot be in progress. So it was, and the foundation stone was laid down by the Deputy Prime Minister Sardar Vallabhbhai Patel, and on 21st January 1950. So the building was formally opened on that day. So, and the first director of NPL was Professor K.S. Krishnan, who was the student of Sir Recently, a revision of SI units took place based on the redefinition of the kilogram, meter, ampere, Kelvin, and mole in terms of well-defined, precisely measured basic constant, that is Planck's constant, h, velocity of light c, L, and charge E, Boltzmann constant k, and the Avogadro number. And otherwise, actually, the old standards of meter and kilogram were based on the platinum rod and platinum iridium alloy cylinder kept in BIPM Paris. So every year we used to go and calibrate our prototype kilograms and this 1 meter length platinum rod. So now there is no such need. It is well defined based on the fundamental constant which can precisely measure in any good laboratory. So this is about the NPL. I will not go into details. So the major activities, one of the major activities of NPL is to establish, maintain, and improve national standards of measurements under Weights and Measures Act 1956 and followed by 1976 Act. This is the only laboratory which is written, whose mandate is written in the Constitution of India. And there, this is the main mandate. Of course, we have many other several activities like materials development of various novel materials, and there are many characterization facilities, name anything, it will be available. And these are not only for the NPL projects, but also they are useful for the outsider also, or any institution or any academic or defense laboratories like that. And there is another interesting thing in this activity, that is planning, preparation, and dissemination of certified reference materials. Suppose you have a sophisticated analytical instrument, so you have to check from time to time. So by taking or purchasing this type of CRMs from NPL, you can check your instruments like that. And the another important activity is radio and atmospheric sciences. In this estimation of a greenhouse and other toxic gases are here. Just a minute. So that is in Antarctic environment studies also is an important activity of this division, radio and atmospheric sciences. And so I would like to for a just to have some understanding at what accuracies the standards are maintaining. I would like to share with you as an example. I am telling about the time standard. This is the CSR NPL's one of the world's most accurate cesium fountain clock. It is actually its accuracy uncertainty is 1 in 10 to the power 14. In a simple language, we can say that the clock may lose or gain only 1 second in about 40,000 years. So that is the type of accuracy that the standards are maintaining at NPL. It is based on the transition between the cesium 133 atomic transition between F is equal to 4 and F is equal to 3. So according to this, we can define 1 second as 9,192,631,770 periods of the cesium 133 for a hyperfine transition of F is equal to 3 to F is equal to 4. So the basic principle is explained in the schematic here. So the time signal is actually produced by the solid state microwave oscillator, and its signal is corrected by the atomic reference, that is cesium 133 atomic transition. And if there is any error, it will go to this, and with the feedback mechanism it will be corrected. And of course this time also the NPL is used to compare the international NMIs, and such a signal is giving to the country and the world even. So this is the type of accuracy at which the standards are maintaining at National Physical Laboratory. So now we will come to the today's talk of characterization of nanoparticles or crystallites or pimples and their structures. The stringent properties of modern devices emphasize the need of accurate evaluation of composition, including purity or trace elements, crystallographic structure, and crystalline perfection. Nanoparticles or crystallites, thin films, and their structures are to be characterized to get their quality, size, composition, morphology, etc. In view of this, the talk is designed with the following outline. Of course, actually, I have some bias about the students of materials and metallurgical engineering students. So keeping for these students, I have covered something like 80% of the techniques which are actually needed for the MME students, either PG or UG students. So so of course there are other techniques also, other important techniques for to complete this characterization for the nanometals. Of course there are so many varieties of techniques. Because of the lack of time, even though they have given 1 hour 30 minutes, it's a very good time actually. So there are many more techniques actually. So maybe at some other occasion I can cover some more techniques also. So today we have some 5 techniques for the elemental analysis by sophisticated analytical instruments, and the structure determination by X-ray methods that covers essentials of X-ray crystallography and other 3 methods. Then study of functional groups and their structural or order desired details through vibration spectroscopy. That is FTIR and FT Raman spectroscopy. Then FESM for morphology, topography, distribution of nanoparticles or composition in a localized area, and characterization of nanoparticles or crystallites, and polycrystalline thin films by epitaxy and HRXRD, and reciprocal space mapping, etc. And also the quantum belts and the grazing incidents in plane direction for varieties of structures and nanofilms, and of course X-ray reflectometry also I am going to cover. So then at the end, some summary and conclusion. So okay, so the first there are five elemental analysis techniques I would like to cover. So these are having the almost the same basic principle. This underlying principle is as follows. In each element, the atomic structure has a unique electronic configuration, and each electron has a specific orbital or binding energy, and hence the binding energies of the photoelectrons ejected from the energy shells or orbitals, or the radiation that emits from the atoms due to transition of electrons from higher to lower energy orbits, are characteristic or fingerprint of the element from which they are emanated, and thereby one can identify the element. So in case of XRF and EDS, measurement of the energy or wavelength of characteristic radiation is involved. In XPS, that is X-ray photoelectron spectroscopy and OJ electron spectroscopy, measurement of binding energy of photo and OJ electrons respectively for these two techniques are involved. And in the AS, measurement of absorbed characteristic radiation in cold atomic aerosol. So it is either emitting radiation, we are actually dealing with the emitting radiation or electron. Here the absorbing of the characteristic radiation is involved. So the basic law which governs all these things are, it is Moseley's law. According to this, square root of the characteristic frequency is proportional to the z minus 1. Z is the atomic number, and C is a constant for a particular series like a K series and other beta series and so on. So therefore, this is the basis for the characterization actually. So now let us come to the first technique, that is X-ray fluorescence spectroscopy. So in the sample, you may have variety of elements, and they will, when we excite this sample, we will get a characteristic radiation from all the elements. So at a time, you will have many characteristic radiations belonging to the different elements present in your sample. So the detector cannot analyze and all these if you are giving all these radiations at a time. So we have to use a analyzing crystal, that is a monochromator crystal. In this, depending upon the Bragg angle and the wavelength of the characteristic radiation, it can diffract only one characteristic radiation at a time. So the detector always get only one characteristic radiation at a time, depending upon the angular position of this analyzing crystal. So by changing the angle of the analyzing crystal, you will get different peaks at different angles are corresponding to different wavelengths or energies. So here, in fact, only one single crystal cannot be used to analyze all the elements present in the periodic table. So we have a set of nine crystals here. Automatically, the instrument will scan the radiations by rotating these crystals one after the another, and the data will be stored in the detector. And finally, the intensity versus the wavelength will give the spectra. Here, what we are measuring actually, angle practically we are measuring, but 2D sine theta is n lambda. So D of this analyzing crystal, you know, theta you have measured experimentally, so lambda you can calculate. So therefore, this is the counts versus the wavelength, or you can convert into the energy also. It is one and the same. So here we have the system. We have the system at NPL at a below tube geometry. This is a special version. The tube is X-ray tube is below the specimen, so that we can characterize not only the solid samples but also the liquid samples also we can characterize. That is a special advantage of this thing. So when I was there, we procured this thing, so it is working very well. So you can characterize the liquid samples also. For example, this is a typical example of determining the calcium concentration in ppm in water sample. This is a deionized water. This is from a pure water purifier RO, and this is AquaGuard purifier, and this is a simple tap water in the same laboratory. So you can see that you can have different concentrations of calcium, which is also needed for the body. So here we can use this system for a liquid sample, and also it can give a mapping also. For example, here with a silicon wafer, the silicon wafer, which is nearly perfect, but still, just please wait 15 seconds. Sorry for the interruption. One important phone call was ringing all the time, so I have hand over to my daughter. So okay, so I was telling about this mapping of silicon wafer. This is almost nearly perfect silicon wafer, but still there may be some the impurities which may be in the ppm level. So we can not only identify the elements quantity and also with the quantitative estimates, but also we can have a mapping how they are distributed on the wafer. So they have a different elements have a different distribution in the silicon wafer. So that type of things one can do with this X-ray fluorescence spectroscopy technique. And it is an analytical tool for qualitative as well as the quantitative elemental analysis, and it offers fairly good performance over wide range of periodic table elements, that is from beryllium to uranium. So of course with the beryllium, because the window is also made with the beryllium, so we can accurately get good results from boron onwards. So like that up to uranium. So you can do very good characterization for many samples actually, and they may be in the in any form. They may be solid, powder, liquid, fusion product, thin film, slurry, alloys, steel, ores, and they may have any shape also, no problem. So, but there is some there are some limitations here. So the standard actually suppose a light material, that means Z is less, atomic number is less suppose for one element, and that is embedded in a sample of a high atomic number, then the accuracy of the measuring the quantity may be slightly different. So for that purpose, you have to make a standard sample close to that of the reference sample, test sample, and in that you can get a very good accuracy, And however, a semi-quantitative analysis also there. It is this program is within the instrument, and that it will correct for the intensities of these different elements. when they are present in different matrices, and therefore you can get a with a good accuracy finally, even though you do not have a standard sample. Of course, with a standard sample, you can go up to the even very any sample also with a meager amount also up to ppm level. Why we cannot study the below boron is because of the fact that this fluorescence radiation is very less for the light elements, whereas but in case of a OJ electron spectroscopy, this is very good for the low atomic elements also. So I will tell you more details in the coming slides about the OJ electron spectroscopy. So this is about the energy dispersive spectroscopy. So the basic principle what you have seen is the same, but only thing is here we are measuring the energy of the characteristic radiation. Here we are also using the SEM electrons. Here we have, suppose you have a FESEM, by attaching this EDS facility, you can determine the identify the element, and also you can determine the quantity of those various elements. And we are using the electrons from a SEM gun. So that is the thing actually what we are doing here. So here the sample is bombarded or excited by a electron beam of a SEM instrument, and now because of these excitations we are getting the characteristic X-rays, and this is detected by a solid state lithium doped silicon detector, and each photon depending upon its energy will convert into a charge pulse, and this charge pulse is converted into a voltage pulse, and finally through this amplifiers and all you will get a voltage intensity versus voltage, and the peak position will give you the identity of the element, and the relative intensity of these peaks will give the relative abundance of the elements present in the specimen. So this is actually XRF is a bulk technique. It is a bulk technique because X-ray can penetrate inside the sample to several microns. So it can be used for a bulk technique. Like suppose if you want to know the purity of a gold, this is the best technique. And here one can go up to the in EDS you can go up to 1 micron. So you have to use a particular technique as per your requirement and as per your sample condition. So this is also useful for the elemental analysis, and trace elements also can be done. Phase identification and distribution also can be done in this also. And of course here also there is a limitation for lighter elements. Lighter than carbon cannot be tested by this, because the results will not be very accurate, because its sensitivity is only it is around 0.1 weight%. So you have to really know at what percentages. If it is for a trace elements, this may not be very good technique, and there is also a poor sensitivity for lighter elements in a heavy matrix, as for the X-ray fluorescence also, and resolution of the X-ray energy levels limits the positive identification of certain elements. Suppose molybdenum and sulfur both are there in your sample, and some energy levels will be overlapping. In that case, is a bit uncertainty in estimating its quantitative values of these two elements if both are present at a time. So again, if you have a standard sample, such problems also can be eliminated. So this is a typical example of a EDS spectra. In a KHP single crystal, we have doped magnesium and mercury. Of course, one has to realize that whatever the concentration that you are putting in a solution or a melt, so that much concentration of these dopants will not go into the crystal, because the crystal has a tendency to reject the impurity atoms or any foreign atom for that matter. So again, you have to test by some elemental technique either for XRF or EDS or AAS like that. So here, for example, in case for a 1 mole percent magnesium doping, we are getting only 9.16 ppm. And similarly, for a sample with a 20 mole percent of Mg, we are getting sorry, the 12.67 ppm. And for Hg, we are getting only not 9 ppm only. So like that, you have to, of course, sometimes you may not actually, we could not get it from this spectra actually here, but AS has given a good value. So sometimes if it is not in the up to the 1 micron surface, again this may not give. AS of course is a very good technique. You can it can go, you can do the bulk characterization also. So the next technique is X-ray photoelectron spectroscopy. When a photon of energy hits an atom, the electron ejects from the well-defined electronic orbit with a certain kinetic energy, with which the binding energy can be calculated as using the already determined work function of a system. That means, suppose if you hit the sample or excite the sample with a high energy X-ray beam, or for that matter an electron also, one of the core electrons will eject from its shell, and because now this is an excited state, it is very unstable in this condition. Immediately, one electron from the next outer shell will come and fill this gap here. In this process, it will emit an energy equivalent to that of the difference of these two levels, and that is actually we are okay. So here actually we are getting the photoelectron. That energy is corresponding to the characteristic radiation, but here we are in fact studying the photoelectron, that is whatever the electron that is ejecting from this, we are concentrating on this electron as such, not with the energy where we have studied this energy or the wavelength in case of XRF and the this EDS. But here we are looking for the photoelectrons here, and these photoelectrons, depending upon this energy and these orbital energies of these two this level, it will have some kinetic energy. So of course it should be incoming radiation, it should be more than the orbital energy of this particular shell, and the photoelectron will have the kinetic energy, which is which is governed by this equation. This this orbital energy that is equivalent to the h nu, that is the incoming radiation energy, and the E kinetic energy. So what are the kinetic energy with which the electron has emitted or ejected from the atom, that one, and it is a work function of the machine, not the. So if once that is calibrated, you can easily get this EB, that is the orbital energy, and every atom has its own orbital energies for different shells, and therefore this is again the fingerprint of the particular element, and this is the experimental setup here. Here the sample is excited by a soft X-rays, and the photoelectrons are emitting, and these are focused to this concentric hemispherical analyzer. These are the two electrodes. Their shape is hemispherical, and only a few electrons whose energy lies in between a small range, they only come to this other end. Otherwise, they will hit these electrodes and they will not come to this exit slit. And these are going to the electron multiplier, and you can get a this spectrogram, and the intensity, the position will give you the identity of the element, and the relative intensities of these peaks will give the relative abundance of the those elements present in the sample. Excuse me. So this is an example. It is the X-ray photo electron spectroscopy of some carbon nanotubes. Here you can see when the carbon nanotubes are actually first they exposed to the ambient. Then in the ambient, as you know that oxygen and nitrogen are very high. So they have actually contaminated by this nitrogen and oxygen, and the actual peak for the carbon is much less than the impurities. So when it is purified, then only you are getting a good peak for the carbon, which is supposed to be in the carbon nanotubes. And whereas this the peaks due to oxygen and nitrogen are very, very less. So like that, you have to be very careful when you are in the nano region. So because you have a very nano surfaces or nano particles like that, so you have to have a protecting layer also in some of the cases. So you have to be careful. So this is the fourth technique, that is OJ electron spectroscopy. It is a three-state event. Here, from any high energy electron or a photon, you can you can eject one of the core electrons, and this core electron will be filled by the first outer shell electron, and you will get a some characteristic radiation that whose energy is the difference between these two shells, and this energy will be used to eject one electron from the second outer shell. So this is called OJ electron. Actually, you are now studying the OJ electrons instead of this ejected photoelectrons. So here, what is the advantage of this? Actually, these electrons also carry some information about the ionic state of the element, what you are studying. So for that purpose, you can use this OJ electron spectroscopy, and these are these are having very small energies. Therefore, they can also use for a very surface. That means mono layers or few layers you can study, like we have learned from the earlier speaker about the LB films like that. So these are this type of this OJ electron spectroscopy is very good for such a thin layer, to characterize the thin layers, right? So the instrument, okay, this experimentally you are studying this, you are measuring the kinetic energy of the OJ electron. From that, you can actually, this is the energy of the core level, and this is the first level, and this is the second outer shell energy. So this will modify if the atom is in a ionic state. So that also you can compare with the standard values for all the specimens, and then are the elements, and then you can not only identify each element along with its quantity, but also you can get the ionic nature, suppose something +1, +2, or -1, -2, and so on. So the instrumentation is like this. Here, the sample is kept here and on the target, and there is an electron gun. The electrons hit the sample, and thereby the the sample elements, different elements are excited, and they will eject the OJ electrons, and they will go. There are some holes here, windows are there. These are the two cylindrical mirror analyzers with two electrodes, and depending upon the potential applied, the potential difference applied between these two cylindrical shells, they will different photoelectrons will come to this end. That means at one time, depending upon the voltage difference between these two shells, so only a few electrons whose energy lies within a very narrow energy band, they only can come here. Otherwise, others will not reach here. So they are amplified, detected by a electron detector, and the signal will go to the data acquisition system. And here, in addition to the OJ electrons, there are many other electrons also. So generally, noise is very high in case of this OJ electron spectra. Therefore, by applying this alternating voltage, that is the sweep voltage, so you can go on chain this, keeping the difference same. You can vary this potential between these two electrodes, and by applying this oscillating, that is alternating voltage, then you will get a good signal. Actually, you can identify the signal of a particular element what you are going to study with good accuracy. So it often runs in the derivative mode. That we call it as a derivative mode to get the peaks very clearly, so that you can measure this various element present in the sample. So this is a typical example of a AES imaging. By using one ion source, that is ion gun, you can etch the different layers. You can etch the layers, layer by layer you can etch, and then you can have a depth profiling also with this technique. For example, in case of this, it is an example of again carbon nanotubes, carbon fibers actually. So here you can see on the surface some of the oxide layers etc. are there, like oxygen and nitrogen, like that. So they are contaminated. The very surface is immediately reacted when you open from the chamber after its growth. So you have to first remove the first layer, and then you can study the other things. So here these are the carbon fibers. You can see pictorially also. This is a AS imaging actually. You can scan the sample, and you can get the various elements present at different depths. This is the intensity versus OJ electrons versus the sputtering time. So when the sputtering time is less, means we are at the surface only. When the time goes, you are going deeper and deeper. So at the very surface, you have many impurities, but at when you are going inside, that means just after one or two layers, you are getting the only one signal, that is almost the carbon is the main thing, because carbon fiber is supposed to have a carbon element only, and this will be very less inside this sample. So like that you can do the characterization of these elements, not only the elements but also the very nano films also one can characterize with this technique. And this is the other technique, that is AAS, that is atomic absorption spectroscopy. So here it is again a bulk technique, and the energy levels of atoms in their atomized state are quantized and unique for each element. So when the frequency of the incoming radiation matches with the characteristic frequency of an atom, the atom in its ground state absorbs the radiation and thereby the element is identified. So you see how this absorption factor you can get. Actually, suppose you have to take this this atomic aerosol. That means they should be in the atomic state and they should be at a very low temperature. So cold condition it should be. Then when you are passing a light of white radiation, and you will get some absorption lines, that is dark lines, because the absorption when once the absorption takes place, it will also emit after emits, but they will emit in all the directions. Therefore, in this direction, the intensity is very, very less, and it is as good as no intensity. So therefore, you are getting a dark lines on a white background. So that is the how you can get the absorption. The theory is like this. So in this manner, light of characteristic frequency of the concerned element is passed through the atomic aerosol of the sample, wherein the atoms absorb the frequency. As per the Lambert and Beer's law, IT is equal to I0 e to the power of minus alpha LC, where here I0 and IT are the incident and transmitted light, and alpha is the absorption coefficient, L is the path length of the radiation along which it is has passed through the sample, and C is the concentration of the atoms in the solution, like that. So the absorption you can get by taking a log for IT by I0, and it is equivalent to minus alpha LC. So more the concentration and lesser the transmission, and like that you will get a minus sign. It is only a notation. So the working is as follows. Actually, it the important component of this AS is the atomizer, or a nebulizer also you can call. So it consists of two coaxial tubes. From the inner tube, the sample in the solution form is actually passed through this inner tube, and from the outer tube, a mixture of acetylene and air will pass here with a high pressure. So because of the friction of this atomic solution, they will first form into a mist, and because of the acetylene fuel, it will burn. And now then a characteristic radiation passes through this sample aerosol, and some of the characteristic wavelengths or the waves will be absorbed by this sample in its means atomic form, and then you will get some, of course, will go transmit, and some will be absorbed. We call it as a percentage of transmission, and the detector can determine the percentage of transmissions. So from this absorption coefficient alpha, it is very important that you can measure, and also actually finally you can get the concentration. Here the important thing is, suppose you have a few elements, each element needs a one this is called hollow cathode tube. Yes, and because it should give a characteristic frequency of the same element which are going to test. You should have a variety of this hollow cathode tubes, and at NPL of with our system we have some 67 elements are there. HCLs, that is hollow cathode lamps, are there. That is 67 cathode HCLs are there to determine 67 elements. So because suppose hydrogen and helium, they exist only in the gaseous form, so you can't make a filament. So therefore that is the limitation. So one should know what are the limitations and what are the plus points or characteristic features of a particular instrument or of a particular technique. Then we have to use such techniques. So here we have determined the chromium doping in a ZTS sample. Here for 1 mole percent, we got 45 ppm, and for a 2 mole percent sample, that means in the solution we have added 2 mole percent of chromium. But what is the outcome? What is actually gone inside? It is very, very less. That is 55 ppm only. So like that, unless until you study the elemental analysis, you can't really predict by simply adding something. So therefore, these are very important things and important techniques to really know the characteristics of your sample, which finally depends on the your property that is you are expecting. So next we are coming to this FTIR and FT Raman. So before that, we should know something about the vibrational spectroscopy. You see, in a molecule, so in addition to this specific energy levels, you will also have rotational, vibrational, and vibranic. That is a combined vibrational and electronic energies. That means, you see, in a molecule there are some atoms, right? Suppose there is a triatomic molecule like here. So these atoms are not stable. They will go on vibrate, and these are also, they rotate. And out of all these things, vibrational energy is the much more. Therefore, we are interested to study the vibrational spectroscopy, and these actually these have very certain energies. For a particular molecule like CO2 is there, so the C and O2 oxygen atoms are there. They have a particular vibrational energies. So depending, and it is a fingerprint of that molecule. You may have some sub groups also, functional groups, etc. So all they are having their own energy levels. So these energies are very close to each other, because there are variety of vibrations for these atoms are there, I will tell you. And these energies fall very close to the infrared region. So therefore, infrared radiation is very useful in the vibration spectroscopy. So here, just for your understanding, for the learners, I am telling you. So in a triatomic molecule, you have a symmetric stretching. So both the atoms are stretched with the same length, and they may come back, they may go and come back equally with equal distances. That is called symmetric stretching. Here, this is asymmetric stretching. One is coming close to the central atom, and another is going the opposite way. So that is called asymmetric stretching. Here, this is in plane scissoring. So these two atoms, they are moving like a scissor, and here this is in plane rocking. So both are, without changing its angle, both are actually moving like this. And here there is a out of plane staggering. So the angle is same, but these are moving like this. And similarly, out of plane twisting, you can have a twisting like this. So there are such varieties of vibrations are there, and each vibration is a characteristic of some energy, and that is fixed for a particular molecule. So if we identify the absorption of a particular energy band, we can identify the molecule or its functional groups. So there may be actually IR spectroscopy is very sensitive for the asymmetric molecules. Here, for example, the oxygen has a more electronegativity, so more negative charge on this oxygen atom, and positive charge on a carbon atom. So it has a this dipole movement. It has a dipole movement. So by changing its according to the vibration, there will be a change in the dipole movement. That is actually sensible for the infrared radiation. Suppose there are symmetric molecules like this, alkenes and alkynes, then there is no net change in the dipole moment. So, but there is a overall change in the polarization that also will change according to. So that is all the symmetric molecules may be can be identified by Raman spectroscopy. I will give you more examples and I will explain you more. So this is about the FT, that is Fourier transform infrared spectroscopy. The vibrational energy in wave number may be written as nu is equal to 1 by 2 pi c into square root of k by nu. What is k? This is the energy depends on the bond strength of the chemical bonds actually, and nu is the effective mass of the two bonded atoms, and c is the speed of light. So how it works actually, in IR radiation from a Glober and Mercury vapor lamps, actually both this type of vapor lamps are here as a source and is exposed to the IR radiation for the sample, and part of it is absorbed and the rest transmitted through. So the IR spectra is obtained as percentage of transmission or percentage of absorption versus the wave number. That means IR wavelength. So you have to make this sample in a KBR pellet form, and this sample and KBR ratio should be 1:100. So you have to use such samples. So here I will tell you how it works actually. In this there are two mirrors. This is a fixed mirror and this is a moving mirror here. And when the light is coming from the source through a filter, so there is a beam splitter also. It will reflect 50% and transmit another 50%. So here actually this the here reflected light has gone to the fixed mirror and it will come back automatically. And similarly, it will also reflect from the transmitted beam will be reflected from the moving mirror. It will come back, and both are combined here to give an interference pattern. So, and this such an interference pattern will go through the specimen and finally to the detector. So when depending upon this IR wavelength or frequency, if it is matches with the characteristic radiation of that vibrational bands, it will absorb. At least a percentage of absorption takes place, and the rest of this thing will come as a percentage transmission to the detector. So by knowing this spectra, this is the absorption spectra. For example, it is for a ZTS crystal. So you can get various bands. You see here, it is not like atomic energy spectrum. The bands are very broad here. Why it is? Because we have seen that there are many varieties of vibrational energies are there, which are very close to each other. Therefore, they are mixed. They are mixed, and you will get a broad absorption band. We never call it as a line. We call it as a absorption band or a transmission band like that. So it not only gives such important absorption bands. For example, here in a ZTS carbon oxide bond is there, so it will give a absorption band like this. And this is a urea doped ZTS crystal. This absorption spectra is from this actually. And here what has happened actually, the same C and O are there in the host lattice also. So it is very difficult to estimate the concentration of this dopant by any other elemental methods, because they are sensitive for the elements also. What bond that is having, that cannot give actually either a CHN analyzer or AES, XPS, XAS, anything. It can't really distinguish the dopant values. Through this double bond of the carbon and oxygen available in the urea dopant, we could able to get this bond through this IR spectrum, and you can see that here at low values there is no band, and here they are prompt actually, and that promptness depends upon the value of the amount of dopant. So like that you can get all the information including the dopants from this FTIR. So sorry, I have forgotten to tell the experimental details. Here, as I told you, one is the fixed mirror and another is the moving mirror. So experimentally, what you have to do, just this will go on move, and that movement in 1 second it will move up to 1 centimeter, and in this 1 centimeter movement the detector will take 1000 data points. So therefore these data points are stored first and then Fourier transform, and you will get the absorption spectra in a real sense. And of course you have to take the background also. Without the sample also you have to first run the ratio of the absorption spectra with sample and without sample will give the actual absorption spectra. So what is the physical meaning of this Fourier transformation? Many people do not know about this, particularly the young researchers. I would like to tell the physical meaning of Fourier transformation. So here a detector is there. We have a detector. What it can detect? It can detect a oscillating radiation also, and the output will be the in the form of a oscillation energy. So when one frequency is there, it will give the exact replica as for the incident radiation. But here you have a interference pattern, and you are getting because here in this case to reduce the time, at a time you are exposing the sample with all that white radiation. That means all wavelengths in the infrared region that is coming from the lamps. So Glober and Mercury lamps both are there to give the complete IR wavelengths. So you are at a time exposing the sample, and therefore you have naturally more than one frequency. And suppose there are two frequencies of the same amplitude, suppose let us, and there is a small deviation in the frequency. That means delta F is there. So when they are combining, you see here they are almost in phase, they will add it up. But here when it is come to this point, they are at the opposite amplitude of opposite phase. So you will get a very zero value of the energy or intensity. So you will get a sinusoidal wave like this. Their envelope is again a new a modulated sine wave. So this is called beat frequency, and suppose lesser the difference of the frequency, and lesser the frequency of the beat frequency. Suppose there are 6 wavelengths are combinedly going into the detector, it will like this. So now how to get back the actual spectrum? That is our this thing. So using the Fourier transformation. Now in this case, in the simpler case of adding 2 wavelengths, you are getting this spectra, okay, the interference pattern, and it has some envelope like this. Now what you have to know actually, there are 2 frequencies. That means there are 2 wavelengths, 2 frequencies, and naturally they may have their own amplitudes. So there are 2 amplitudes. So what are the parameters? There are 4 parameters: 2 frequencies and 2 amplitudes. So for this, what generally we will do mathematically, we take 4 components, 4 equations, 2 variable equation. That is, time is the in the time domain you have to measure the intensity at 4 places. That's it. So that is what the detector is doing. And after this Fourier transformation, that means by solving this 4 equation, we are getting the 4 parameters. That is 2 frequencies and their amplitudes. Of course, for the simplicity, we have taken their amplitude as the same. Here also we got the same frequency. Of course, these may not be very line, so these becomes a bands, what we have seen here, and you will get the absorption or a transmission spectra like this. Now, this another technique is a FT Raman. Here, the phenomena of inelastic scattering of light by a substance with different frequency from that of the incident frequency is known as the Raman scattering or Raman effect. So we are proud to name our own Indian, that is Sir C.V. Raman. So with his great son of India, we got Nobel Prize. That is the first Nobel Prize in the Asia, not only India, in the Asia. So this actually gives a Raman spectroscope. It is a complete branch of physics has come out. So this is actually, so there is a difference in the scattered frequency. That is what he basically what he observed. So sometimes that scattered intensity may have the lesser intensity, lesser energy than that of the incident radiation, and sometimes it may be more than the incident radiation. So this is called anti-Stokes Raman lines, and these are the Stokes Raman lines. So how it is happening actually? So we have already understood what is the vibration spectroscopy. Here, the molecules, suppose when they are at a lower energy state, they can absorb some energy which is in the infrared regime, and so they will give a lesser scattered radiation. But suppose the molecule may have is a crystallographer can produce three-dimensional picture of a density of electrons. Actually, this X-ray scattering or diffraction is sensitive for the electrons, not for the neutrons or the atoms. But the electron density represents the position of the atoms, and therefore you can determine the structure. So the chemical bonds, disorder, and various defects also can be obtained from this X-ray crystallography. So why we have to bother so much about this crystal structure? It is from the following example. You have a diamond and a graphite. So both are the allotropes of carbon. That means the composition is same in both the cases. But whereas this has a very strong and very hard, and this is very soft. How it is come? How that difference has come? It in case of a graphite, it is a sheet stacking of sheets. Here, within the sheet, they are covalently bonded each other strongly. But in the vertical direction, there is no strong bond except the van der Waals forces. So they are slippery from one another. So therefore, this is a soft material. So it is essential to know the structure of the any material. So generally all materials they exist in a polycrystal form, even it is a powder. So Bragg has found that there are only 7 crystal classes and 14 Bravais lattices. That means he proved that to fill a space, these are the only 14 ways to fill the space without any leaving any space. So, but nature is very clever, and the quasi crystals are. It is still 1 hour. Oh, I have to go quickly. Okay, so this is a quasi crystals are exceptional in this case. So therefore, so you have to know you have to give the indices for the Miller planes, and there is a method given by Miller. You can find out the Miller indices like 3 to 1 and so on. You can determine the. I'm sorry. Actually, I'm going quickly because still a lot of matter is there. So you can theoretically calculate the interplanar spacing of like this, and you can measure this the relation between the DHKL and the particular HKL planes, and the scattering. There is an ability of an atom to scatter the X-rays. So, but that scattering efficiency or the scattering amount depends upon the angle of scattering. So, therefore, you have to find out the structure factor of a unit cell. That means it is a sum of these atomic structure factors within a unit cell. For example, in a body-centered cubic, you have two atoms by following this equation, and you have to sum these two structure factors of the for this body-centered atom, two atoms, but with a phase angle. So by taking all those things in consideration, you can determine the structure factor. For example, it is a case of a BCG structure. So when H plus K plus L, the sum is even, you will get a 2F. So that means you will get intensity peak here. And when it is odd, the sum is 0. Because minus 1 all to the power of, suppose 2 is even, you will get a 1 plus 1. If it is a minus, suppose if it is a 3, you will get a minus 1 minus 1 minus 1 plus 1 minus 1 will give 0, and therefore such a systematic absences you can find out from calculation of the structure factor like this. So by having this all symmetric absences, we can know what structure you are having. This is the Bragg law, which is the basis for the diffraction experiment. Of course, that is only a condition, but a more rigorous way Love has given a set of three equations. So from this is a Love method in which you can have a similar this diffraction pattern like this, where this is this is a white radiation you are putting here, and because of that, actually there are set of planes here, and one set of plane will give a diffraction points around a circle or a triangle like this, and variety of set of planes will give variety of such patterns. It will the symmetry will give immediately what structure. For example, it is a fourfold symmetry, and you can find that it is a cubic system. Of course, they depending upon the shape of these points. Here they are perfect points. There is no strain in these crystallites in this small crystal, and when they are streaks, you can understand it is there are some strains like that. Quickly one can get the, and also orientation also one can get from this pattern, but it is not not using daily because we have got a advanced characterization techniques. That is the Love one. It is a rotating crystal method. In this, actually, the only monochromatic radiation is exposed to the sample. Suppose if it is aligned along the C-axis, you will when it is moving, this crystal is moving around its the vertical axis, and when the set of planes will give a diffraction point on a horizontal plane. If you put a photographic film in this chamber, you will get a circle like that. That is called zeroth layer. And if they are inclined like this, you will get a downward circle, and some are up. So they will get this type of things by measuring this distance between this zero line and the another line. You can you can really get the, for example, keeping this along C direction from this equation. This is R is the diameter of the diameter, and S is the distance between the zeroth layer and the concerned layer. You can measure this the lattice parameters A, B, C, A, B, and C. So this is for the powder diffraction. You can have because here you are taking this powder for a so you can get a pattern like this for different sets of planes. So you can by measuring these distances, that is the arc length, you can finally find out the Bragg angle. If you convert into this degrees, you will get if you make this R, the diameter of the chamber as R is equal to 180 by pi, you can measure the D values. And in the spectra, you see nowadays you have a variety of detectors for a point detector or a zero detector, zero dimension detector, that is a scintillation counter or proportional counter. You have to scan the detector in theta and 2 theta fashion, and you can have a 2D detectors also. From that, if you take a X cut here, you will get a complete pattern here. And not only that, you can get so many details. For example, it is a breaking here, so that tells the grains are there. Grains are there. Here, some arcs are missing. It tells about the texture. So that means there is a preferred orientation in the crystallites of the sample, and you can do the this is the photograph and this is schematic of product study at NPL, and this is you can do by using this multi-layer films, and by using a graphite monochromator, you can scan the sample very close to the surface. That is called grazing incident. You can you can solve the structures of thin films also. For example, for the LB films, what we have heard in the previous lecture, the powder XRD has not done powder XRD because of the limitation that they are very thin. But in this grazing incidence XRD, you can really characterize such monolayers or some very thin layers as well. So you will get a pattern like this, and you can get a this D values also. So you can also how to solve this structure. You see, for every symmetry, for example, for a cubic symmetry, for all the important plane, you can draw these lines, because D is proportional to A. For a set of HKL, you will get a slopy lines, and experimentally you got the D values. This theta can be converted into the D values, and at each D values you can draw these vertical lines, and they will fall on a horizontal line, and by extending this line you can get the real and accurate value of the lattice parameter. For a cubic, it is only A is equal to B is equal to C. You can get this. This is a way of understanding how to solve a structure, but there are some complicated structures. Actually, there are some softwares. So residual analysis is one of the best. In that, the discrepancy, the sum of the discrepancies divided by the sum of the observed structure factors, that is called a R factor. It should be very less value. It will run for all the possible structure, that is for the 14 branches lattices, and for in which if the R is less for a particular structure, that is the actual structure for the sample what you are going to measure. So as already we know that when electrons and holes are squeezed or confined into a dimension that approaches the Bohr exciton radius, then the band gap will change, and they will take a discrete values, and band gap energy also increases as the size decreases. That is why we get for the same material with the different sizes, you are getting the different colors like that. So the size becomes a very important factor. So by using the same powder XRD pattern, and by determining the half width at full width at half maximum, that is beta, that is inversely proportional to the size of the nanoparticle, and theta is the Bragg angle. From the spectra you can take, lambda is known to you, k is a factor that depends upon the shape and the symmetry of the crystallite particles, and you can sometimes you can have a strain also. So the strain and the size can be resolved by this Hall-Williamson method, and you will get a straight line, and this y intersection point will give the value of the tau, and the slope gives the value of the strain. So like that you can see here actually about a grazing incidence XRD. Here, because of one very special character of a solid material for X-rays, below a certain angle that is known as critical angle for the total external reflection, your intensity becomes 100%. That means for a thin film, when the X-ray is grazing along the surface, you will get a 100% reflectivity when you are below this angle. So by using this technique, you can solve it, and you can also do the phase different phases. Each phase has its own pattern, and you can by comparing the standard data, you can identify what are the phases available in your sample. So this is about the field emission scanning electron microscope. As I have do not have much time, so I will just pass on to the results here. Here actually, if you are this is actually backscattered electrons. Here in this mode actually, because the electrons will really they bounce back when they are interacting with the nucleus. So with those electrons, if you take this pattern, so it is proportional to the Z square. Therefore, it will have a Z contrast in this backscattered mode. In this, it is a secondary electrons where these are the secondary electrons. Their energy is very less. They will give the surface morphology. You can see the depth contrast here. Here Z contrast and here depth contrast. So to do the both type of scattering experiments, you can get a very good details about this this thing. And of course, these are the various details of the microscope. I'm not going to give. This is a typical example of a SEM picture for a crystal. It has some layers. It is a layered structure. There is a small bend which can also see from the high resolution XRD. So by using a good technique, we have made a necking process for while growing this thermoelectric material. We got a very good high unprecedented value of the this figure of merit. So this is next about the thin films. Just I will complete within 5. Okay, I have still some 10-15 minutes. Okay, so this is about the silicon germanium layers. This is a very highly perfect, and it is matched with the substrate, but there will be elongation because here it is squeezed to the silicon A value, but because of its elasticity, it will elongate it in this direction, A perpendicular. So you can determine. So it is in the strained condition which we want actually. So by measuring this A perpendicular and A parallel by X-ray method, so you can know the germanium concentration as well as its thickness of the film. And in the case of a relaxed layer, you have to measure this relaxation parameter R. So this is a beautiful picture. So from the film and the substrate, there are two diffraction beams. So there will be a interference. These are called the fringe pattern. By using a semi-kinematical theory, you can simulate this experimental peaks, and thereby you can get very accurate value of the concentration, germanium concentration, and the thickness of the films, and thereby you can get this is a semi-kinematic model. So in which you can have so many layers of different materials, of different concentrations, and all those things can come here. Okay, so okay, this I will skip. So this is a very important example here to minimize the stress at one place or to share this strain developed by the various this germanium. We have slowly increased the germanium concentration. This is actually the active layer where dopants, etc. will be taken place. Here you have a protection cap layer, and it is a graded layer, and it is a plateau layer. All these things by simulation with that semi-kinematical theory, you can get all these parameters. So non-destructively, you can do all the varieties of things for this thing. This is about the quantum wells, and you can measure various parameters, well width, its composition and barrier width, etc., which are necessary to quantize the parameters or the characteristics. This is a single quantum layer, and this is for the laser fiber optic communication. These are useful, and this is a well advanced GaN by indium in-GaN LED structures, and all the parameters we could able to measure. So it is from abroad. Actually, we could able to get all the parameters from our own instruments, and the software developed by myself, and we could get all the important. That is a reverse engineering what we did, and okay, this is about reciprocal space mapping. In reciprocal space also you can measure the relaxation as well as the composition of the various layers, and it gives a even more accurate values compared to the high resolution XRD. So, but it takes a lot of time. But if you have a 2D detectors, etc., this is also very good. Actually, it won't take much time. So there is another important method, that is the grazing incident in plane X-ray diffraction. We have already seen that when the X-ray beam is grazing to the sample, you will have a good interest, 100% reflectivity. Now, if you add the diffraction also, your resolution will increase. So in this way, you can get a high resolution characteristics, and also by changing its angle, that is grazing incidence angle, you can also go for the depth profiling. The surface, effective surface will be very high when you are grazing the sample, and if you change this angle a little bit, you can measure the different, you can characterize the different layers, and this is a polycrystalline sample having a particular preferred orientation along 111. The perpendicular direction, these are the planes. You see, in this grazing incidence in plane condition, you are getting this 2 to 0 planes, and here in the normal out of plane direction 111. Oh, just time complete. Want like can't you use that? Okay. So this is, you can also do the depth profiling like this, and for various for different grazing angles, you can characterize the various layers in the sample, and this also possible in this. And there is another, the last one, that is the X-ray reflectivity. In case of a thin films, whether they are crystalline or poly or amorphous, this technique can be used, and this is for the composition or the density. So you can measure, and also the surface roughness also can be measured very accurately, because there are two reflected rays. One is from the substrate and another from the film. These two are gone into the, they takes the interference, and you will get the interference fringes, and depending upon its this critical angle for the total internal reflection, that depends upon the element characteristic, actually refractive index characteristic. You can measure this value very accurately, and this fringe width will give the accurate value of the thickness. So you can measure the thickness and also the roughness. So along, you see, this is a sample from some IIT Delhi. Once actually they were confused, they are not getting the good properties for this, and we found that there was one oxide layer of 3.4 nanometer with a roughness of 0.37 nanometer. Like that we have for the substrate and layer interference interface also we have measured all these things. So this is a summary of this thing. So X-rays are very powerful. You can use for X-ray crystallography, XRs, and these are actually XRF is will be up to 1 micron and XPS up to 10 nanometer and AES layer by layer you can study, and AES again is a bulk technique but its accuracy is very high, and these are about the structure. We have used X-rays, and about Raman and this thing you can determine the vibrational modes, and FSM the morphology and the variety of surface features. By introducing EDS attachment, you can get the composition and its variation also. And of course, these things I have not covered here. But one interesting thing, yesterday somebody asked a question about a sputter ionization spectroscopy. Its full name is actually sputter initiated resonance ionization spectroscopy. It is a very sensitive and extremely sensitive technique for elemental analysis up to ppb level. In this mode, the abundant neutral atoms released by the sputtering process are ionized by precisely tuned laser beams and counted in a mass spectrometer. So these are the other summary and conclusions of various GIA, XRD, and HRXRD for characterization of the films, etc. And okay, these are the techniques. They have their own very good features and some limitations also. One should know about the their processes. So one has to use a proper technique for characterization of a particular shape or a particular size and particular elements like that. We have to use. I am very much I am proud to show these slides. I have very good number of people and good number of institutes as collaborators. These are the collaborators at NPL. These are the students, and of course the current student who is doing PhD. And these are the various great people that are associated in our collaboration. Thank you very much. And our current situation is like a watermelon. If you open the green zone, it will become red. And so therefore, stay home and stay safe. And thank you very much for your kind attention. So I am ready to one or two questions. Okay, you have time. So okay. So please, it is time for the question and answer. Oscar Garu?
Yeah. Sir, thank you very much, sir, for your wonderful. Yes, sir, yes, sir. Thank you very much, sir, for your wonderful sessions. So you have done excellent sessions yesterday, and also today. Both the talks were highly essential for the young researchers, sir, and we are very happy that we got an opportunity like 2 lectures from the dedicated fellows like you, sir. So now I request the participants to raise any questions. Any questions from the participants? Please come to unmute your mic and. Yes, sir. Tiwari sir, go ahead. Yeah, go ahead.
There is a question from Amritpal Kaur, and she's asking, could XRD size be greater than temp size? In what conditions?
Pardon? Could XRD?
Sir, she has asked, could XRD size be greater than temp size, and in what conditions that can be?
She wanted to compare XRD and the TEM, right? So actually, okay, size, in fact, any bulk in the XRD, you can use a bulk material. So that means it can be a powder of a few grams or a substrate like a crystal or anything. So there is no restriction for the size basically in XRD, because X-ray can penetrate into several microns, and that is, it will give a statistical average of so many thousands of ensembles, and it will give a average value. Whereas in the TEM, it is a atom, it has a atomic resolution. So, but only thing is, because the electron beam has to pass or transmit through the sample, and and it absorb because electrons cannot go infinite distances. It is restricted to few nanometers or at the maximum a submicron. So therefore, you have to make the sample so thin in case of a TEM, and of course the resolution is very high. You can see the atom by atom in case of a TEM. So, but the average values that comes from the X-ray is very good. They are very reliable, because in the TEM you have to make the sample. There are artifacts while making the sample. So for different purposes you have to use different techniques. Okay, is that clear?
So, yes, sir.
Okay.
So,
Okay.
one more question from Mahalakshmi.
Please.
She wanted AFM, atomic force microscopy, and she asked which is better, SEM or TEM, to find out the particle size.
Particle size, actually, in fact, XRD is the best one out of these two, in fact, because actually, when this also again, when they are in the nano regime, XRD gives the size based on their crystallites. Actually, you see, there is a difference between the particle and a crystallite. Actually, we are interested in the crystallite size. Some crystallites may become a particle after agglomeration, but the properties of the nanomaterials depends upon the crystallites. So for crystallite size, XRD is the best powder XRD you can do. So in case of a SEM, it gives the actually size of the particle. It may be a crystallite, then it is okay. But if it is agglomerated crystallite, then that is of not much use actually. So that way you have to use the TEM. Of course, it will give a complete picture. But again, when it is in a nano regime, these particles, then definitely artifacts will take place, and then you can't expect a very good accurate value of the size with TEM also. But because at different places, again, different size of the particles may be there. But X-ray, as I told you, it will give an average value of so many thousands of such particles. So therefore, that the very reliable data you will get from the XRD when the particle size is in nano size. Okay. Next.
Yes, sir.
Sir.
And sir, can you please speak something on
Hello,
AFM?
sir.
Yes,
Sorry,
please.
sir.
Please, pardon?
Sir, I'm Durgababu, sir. No, my question is...
Okay, please ask.
Sir, actually, the powder XRD, to find out the crystalline size, we need the crystalline size should be in nano region.
Yes.
So the powder sample should be grounded up to a nano level.
Right. No, actually,
so now
there is no point of studying the micron size particles or a bigger size into nano to get this size. You see, that depends on. Suppose if you want to measure a nano powder, then only you go for a size determination. Suppose if it is not nano, you don't want nano, you better study the micron particles and you will get a good information about the structure and its quality. So, because when you are making a nano powders, then your interest is to study the nano. So, in such case, definitely you can study by this grazing incidents if it is in the form of a film, and as such as a powder in case of a normal powder XRD, and you can get the good value when the material is in nano. Suppose if your sample is in a micron size particles or crystallites, so you will you will not get the size information. A good size information you can't get when it is in a microns in case of a powder XRD.
Powder XRD.
Okay.
But as compared to, we are having some advanced TEM machines. Nowadays, the technology is in more advanced in terms of like TEM. Advanced TEM is also there.
Okay.
So, will it better result as compared to powder XRD?
In what way you wanted to compare?
That's
you
the
see,
size of the nanocrystallines.
Nanocrystals, you see, you can study, you can see with the TEM as well. But when it is in a nano size, definitely to make a layer, a thin layer of the nano size, in case of a TEM, it is very difficult. You have to make a film of nano powder or nanoparticles. It is not always feasible. So in such a case, it is difficult to see. But if you are managed that, you can see the sizes of different nanoparticles with atomic resolution. Resolution is very high in case of a TEM or HR10 particularly. But in case of a powder XRD, as I told you, X-ray penetrates in so many thousands of ensembles, and it will give a average and a correct value. So as far as the size is also concerned.
Yes, sir.
Okay.
Yes, sir. Yes, sir.
Okay.
Okay, sir. I know, sir. Thank you, sir.
Next. Any other question? Hello? Hello? Okay,
Hello,
some comments are there. Okay, thank you. So please, I'm happy to answer as many questions as possible, because I expect many young researchers in this, including the students. I wanted to disseminate the knowledge. You see, I have given variety of characterization techniques, so that a person can choose a correct technique, because as I told you, some characterization technique has some limitation for some parameters.
Excuse me, sir.
Please. Okay.
Sir, there is one question from Juhi Kumari. She's asking, ADEX graph obtained from TEM and SEM, which one is more reliable?
No, ADS graph, that is actually
obtained from
a different EDS attachment, whether it is associated with the SEM or TEM. What we are using is, we are using the electrons that are actually coming from the electron gun, which are both are which is available in both the system, TEM or SEM. Generally, it is attached to the SEM. It is easy actually to take the electron beam from the SEM. But as far as the characterization is concerned, the basic thing, it really doesn't matter whether you have taken that electron beam from the SEM or TEM. It hardly matters. You are actually connected with the electron beam. It depends upon the energy and the beam quality and other things. If it is a FESM, the beam quality is very good, and that may give a slightly better results in EDS. But one thing I would like to stress, EDS, as far as the accuracy is concerned, EDS is not that good. As I told you, its accuracy is only up to 0.1 weight percent. So therefore, if there are traces, that means very small amounts in a ppm level or ppb level, EDS is not at all good. But it is a quick method, and which can be attached to any SEM or TEM, and you can do your measurements. You need not to have a separate electron gun. Actually, that is the only benefit. Whether and it is same actually whether you are using through a TEM or a SEM. Okay.
Yes, sir. So one more question.
Please.
Is there any possibility to arrest corrosion on building structural reinforcement by any deposition method?
Yes, actually, some of the hydrophobic materials are there. Through nanotechnology, you can have those things. Nowadays, this becomes very common. And by using such nanoparticles, which are having hydrophobic nature, you can coat them for your things, and they will not allow to keep the dust on them. So as far as the corrosion is concerned, that is a different topic actually. Suppose iron, if it is iron is exposed, you have to, it should not be exposed. For example, you have to use a paint. So for corrosion purpose, you have to use paints like that, and there are very good paints nowadays, and that also maybe added this hydrophobic nanomaterials in that, and then your both the purposes will be solved. That means corrosion will be stopped, and as well as because of the hydrophobicity of that particular paint mixed with a certain variety of nano materials, and no water will stay, and it will control the corrosion in a better way. So you can use such materials actually. Is it clear, sir?
Yes, sir.
Hello. Any other questions?
No, sir. I think that is enough
Good,
for today.
good
Thank you
afternoon,
very much,
sir.
sir. Bhaskar, sir.
Sir, good afternoon, sir.
Please, Deepika, welcome.
Please.
Sir, this is Deepika, physics faculty from R.K.Valley campus, sir.
Very nice to hear.
Sir, thank you for such an informative session, sir. It is always pleasure to learn new things from you. Sir, I have one question from general question. This, if we want
Please.
to characterize any sample from NPL, what is the process? Can you brief us on that?
Yes, actually, you can go to the NPL website. There, actually, some instruments are available for a general public, and the cost also written in those in the websites. And suppose if some instrument is not working temporarily, that also is mentioned in the website generally. So you can pay such amounts, and you can get your characterization done. And also sometimes it is possible, because these characterization techniques also are costly for people who are working in some colleges, etc. So they may have some collaboration also. For example, if you have a collaboration, if you make a say, if you do the synthesis part at RK Valley, and if you wanted to characterize and analysis your samples, you can have a collaboration. In that case, indeed, you need not to pay. Such exceptions are also there. I have characterized for hundreds and even thousands of people during my stay at NPL. Of course, that was with my own developed instruments, so nobody can question on me, and it does not require any maintenance charges also. So therefore, there was no pressure on me to earn money from that system. So there are some exceptions if you have a collaboration, and in that case you need not to pay also. But otherwise, these are informed in the websites for each technique, how much is the cost of a characterization of a particular characterization of a particular instrument. Again, in the same with the same instrument also, you may require only one parameter, sometimes maybe three parameters. Such things are also possible. You can see all those details in the website, and you can contact a particular person, which are also given as a data in that, and you can get your things done. Okay.
Okay, sir. Thank you. Thank you so much, sir.
Okay.
It's nice to have you, sir.
Welcome.
Hello, sir. Hiwari, sir, there are two questions in the chat box. Can you read out?
Please.
Hiwari, sir.
Sir, who posted that?
It was posted in YouTube.
YouTube was nothing was there. Okay, I'll just wait now. Bhavanand sir?
No. Hello, sir.
I'm reading.
It was posted in the
Yeah, I'm
YouTube.
reading.
I posted in Google Chat. You just check.
Yeah. Okay. Thank you,
You
sir.
can
I
you can
just
say in
saw.
Google Meet. Ah.
Yeah, I just saw that. Thank you, sir. Bhavanand sir?
Please.
Hello? Two
Hello.
questions are there.
Please,
How do
please
we
ask.
see PSA technique? How do
How
we
do
see
you?
PSA technique vis-a-vis SEM, TEM, and XRD? And is there any precise way to determine thickness of the thin films?
Yes. There are variety of methods to determine the thickness. Suppose if it is a crystalline film, and again in the crystalline film, if it is a nano size or a micron size or a millimeter size, the technique that you have to choose is different. For example, in the nano films like LB films like that, so you have to go for a grazing incidence XRD. Okay, what I have covered in my talk, I spent a good time also for that. So you have to use for a nano crystalline films, you have to choose grazing incidence XRD. Okay, and if it is in a even in a microns or even in a millimeters, you should go for a high resolution XRD that is combined with epitaxy with good amount of intensity for the incoming beam should be there. So that is through epitaxy method by HR high resolution XRD, you can do the thick films. You can do for the thick films. And there are another class. They are not epitaxial, they may be amorphous also. And many times, like this nanofilms, sometimes even that LB films also, you cannot make an epitaxial. So, in such a case, you can do this X-ray reflectometry, for which I could not spend much time, but that method is good for both epitaxial films as well as the amorphous films. So, in case of amorphous films and thin or thick also, particularly thin films, so you can do the X-ray reflectometry. So that way you can measure their thickness and the interfacial roughness and the composition of the various elements present in the film. Also, you can get that depends upon the technique. For example, XRR, you can get the composition or the density of the film. Suppose sometimes you may have a porosity and you can get the density if you know the composition. Suppose if you measure the density by some other means, like then you can get the composition also. So like that, and that is XRR as well as the epitaxy methods. You can also get the interfacial roughness also. So these are very important when the size is becoming so much miniaturization. So all these parameters like roughness in the interfaces or in the very surface, this becomes very important and crucial to know, to estimate the device parameters, device characteristics. So therefore you have to choose a particular technique for a particular parameter. So that is why actually a person who is telling for different varieties of techniques at a time, so you can get more comparative information from one technique to another technique. So that is why I have chosen this type of a good number of characterization at one talk. So I am happy that you people have kindly allotted a good amount of time in both my lectures. So that is why I could able to compare different methods, either the growth methods or characterization methods. So next question, next sir, another question you have?
Sir, what is
Sir, there is a
PSA
general
technique?
question.
Please.
Yes, sir. Go ahead. So there is a general question in the YouTube.
Please.
What is the future generation of nanoelectronics? It is asked
So
by
it
Satish
is,
Kumar in the YouTube.
it is very, very, very important question. I feel happy to know such interesting facts. I'm really happy for this question, though it is a very general. I would like to say that actually now we have the microelectronics, the chips, the chip technology, and all those things are microelectronics. Now in the future, the things are very miniaturization, and nowadays in a smartphone you can see the TV type of picture and audio, everything. Similarly, in the coming decades at least, nano electronics will come. In the sense, actually, to make a transistor, you need a you really does not require a much space. Quantum dot, a single quantum dot transistors are already invented. That means the active region, that PN junction, is now a dot only. So you can imagine how miniaturization our future things, future electronic devices and all these things, you will have further miniaturization, and you can carry everything with you. Nowadays, within a single pen drive, you can carry your whole thesis and so many things also. Suppose, for example, if you have a lithium niobate single crystal, you can store 10 to the power of 9 pages. That is why our pen drives or even computers, they became so miniaturization, and even everything is there in the what we were having in a laptop. Now we are having everything in the smartphones. So like that, the phone may be replaced by something in your wristwatch. Everything will be incorporated in a wristwatch size of device. Everything may be there inside. So in this nano electron, in the nano technology, I'm sure will lead to, not may lead to, will lead to nano electronics with further miniaturization of this gadgets, electronic gadgets. Definitely it will be there, and a lot of research is going on, and it is very interesting, particularly in the medical science, for a diagnosis and even treatment, drug delivery, and all those things. There are tremendous scope to improve our. I can give a separate talk of 3-4 hours also about this complete nanotechnology. That means actually I have not covered the properties and the fundamentals, the properties and applications of nanotechnology. I could not touch in this 2 lectures also, but I can give 2 more lectures. One will be on the various properties of nanomaterials, and because there are novel properties and novel applications, and energy is again another sector which is very promising. With through nanotechnology, we can have sufficient energy almost free of cost, using the sunlight actually. Now in the future, we don't have any scarcity of the electricity. So this is what I guess actually, and it will be true. It will be true. So there is no exaggeration that I am making actually. It is a question of time actually, both in medical and even automobiles, aeronautics, satellites, so many things. This nanotechnology is going to change our lifestyle altogether, a different one. Okay, sir. Any other question? I am happy to even answer some more questions. You can ask like this any general also. I will be happy. the purpose of such conferences is for interaction. Actually, you will get confidence if you clarify your doubts, and I am really very happy that some nearly some 200 people or something like in the Google Meet, and there are many others, something like 800 in the YouTube, etc. It is very nice actually. It is much more benefit than a physical and real type conferences, because we are covering enormous number of people without spending any money for this. It is really a useful thing that webinars are very useful actually. This is what that COVID-19 has given to us, this lesson. Okay, sir, please ask any other question if you have.
Good evening, sir.
Please.
I'm Mahalakshmi from Chennai. You have drawing the graph only by Argin. Is there any software other than Argin, sir, to draw the XRD graph and all?
I couldn't guess your question actually.
So drawing the graph for FT and FTIR and XRD, we are drawing the graph, sir. We are using the Argin software.
Yes, we are using.
Is there any other software to draw the graph, sir?
Yes, Argin software is good enough to do anything.
Okay,
even your 3D graphs also you can get through Argin. Actually, there are versions, higher versions, they will give 3D graphs also.
Okay, sir. Okay, sir.
It is good for a scientist or academicians. I think Argin is good enough. You need not to go for so many other versions, other softwares. Argin is good enough. It is mostly freely available in the internet. You can download and you can use it. So, any other question? Tiwari garu?
From my side, it's done, sir.
Sir, I think the questions are over, sir. It's over.
Okay,
sir.
very good. Okay.
Questions
I
are
am
over.
very happy that I have interacted a good number of audience, and once again I am thankful to the organizers, particularly Bhaskaraya and his team, Tiwari, and so many people are there. So it is a very good thing. I hope this type of webinars, because you need not to spend anything, and the people like me are available at various places. They are free also. You can arrange this type of webinars, even more also. So I am always ready to give this type of webinars. And thank you once again. And I congratulate all of you for a successful organization of the webinar. Okay.
Hello, sir. Hello, sir.
Please.
One question, sir.
Please.
I got a data for my question.
There is a noise actually. If you okay, can you please again repeat?
Hello, sir. Can you hear me? Sir, I got the XRD data for my sample. It's a lanthanide series element, but sir, one problem is that the XRD data is very noisy. Then smoothing, smoothing, but up to which level I have to do it for the more number of peaks that I can assign for the 2 theta value opposition?
Okay, actually that depends upon the quality of the powder that you have made. Actually, it should be a micron or submicron. The particle size should be, and if it is a uniform, that is better. And okay, if it is not a good quality, you will not get a sharp peaks and more peaks, and the low.
Sir, up to hello.
Made and all those things. you can get a good peaks. But however, again, if you want a number of peaks more, the scanning angular range should be more. So it again depends upon the quality of your crystal or crystallites that you are going to study. That is the
The
most important.
peaks are uniform and they are symmetrical, everything, and they are intensive. Everything is okay, but the noise, or you can say the background, is high. So, is there any way to refine it again, or up to which level to standardize my data?
Okay, actually, there is one parameter that is sometimes K beta also. It is actually fact K beta and K alpha combinedly you use in the powder XRD, and there is a software you can reduce the K beta intensity up to a great extent with the software itself, and you can get a good peaks. Actually, good peaks means sharp peaks. So, you suppose if you is it a powder sample? You have a powder sample, right?
Yes, sir. Okay, sir.
Okay. So in that case, actually, suppose if you grow some film and if it is having a preferred orientation, then you may not get a many number of peaks. But what are the peaks you get? You will get the whole information. It is not required to have so many peaks if the quality of the peak is good. So for to get a good quality of the peak, first of all, your material should be a good crystalline nature. And another one is if you choose a, a unique size particles, that means some if it is mixed with a nano and a micro and all those things, you may not get very good sharp peaks. Sharper the peaks, better the quality of the structure or structure determination, etc. Is a good. It will yield a good parameters actually. That is the
Yes, sir. Sir, very nice. Sir, you said that not a large number of peak, matlab, it's a 4 and 5 peak, but all are very matlab, intense peak and uniform peak, or you can say fine peak. So I can explain that data, na? No need to again. I have to do XRD or anything.
Yes. Sure. You need not to go for so many peaks. If the quality of the peaks are sharp enough, then those 4 peaks are good enough to identify. You compare with the standard PD standard data, you can get the structure whatever you want. So
Yes, sir.
you can
And sir,
get
what software you are telling about? Which software you are telling about for refining K beta value?
Actually, there is no separate software for the K beta suppression of the K beta lines. So they are also embedded. One parameter will be there. Suppose sexual is there, or retrieval model is there. There another parameter is there inside that program. You have to choose that. Automatically, it will be subtracted to a great extent. There is no software separately for the K beta removal. Whatever the software you are using, mostly all those softwares are containing this facility. You just verify that. It will sometimes ask actually, and you can.
Okay.
Thank
you. Thank you so much, sir.
Okay. Welcome. Any other question?
So thank you, sir. Thank you very much for answering the questions.
Okay.
So like this, as you said, we can have exclusively like maybe 2 more talks in the maybe for the next webinar exclusively on the nano related from your side. So we'll be happy for that and.
Yes. Sure. I am ready.
And yes, sir. Okay, sir. Thank you very much, sir.
Okay, thank you.
Thank you, sir.
Namaskar,
Thank you
sir.
very much. Thank you very much, sir.
Thank you.
Tiwari, sir.
Namaskar, sir.
Yeah, okay. Shall we close?
Yes,
So
sir.
we'll have one announcement to the participants. So, yeah. So,
Okay, sir.
thank you all. Thank you all for your active participation. And today the session is over. And tomorrow the session starts at 10 o'clock. So I request all of you to join at least 20 minutes before. We will send the links to your registered mail ID and also to your WhatsApp groups. Thank you. Thank you, one and all.